Hi, very good morning to all.
Good morning, sir.
Good morning, sir.
And I think 23 participants are here. Fine, I think we can start now. So the agenda for today's session is we are going to discuss about ensembling techniques. So what are different ensembling techniques available? What is really the advantage of ensembling techniques compared to other machine learning models that we have discussed as of now in this course? And also, out of different ensembling techniques, we are going to do our discussion with respect to one ensembling technique in detail in today's session. Of course, if time permits, we are going to discuss this another ensembling technique also in today's session itself. So yeah, mostly today's discussion will be on ensembling techniques, ensembling based machine learning algorithms. But before going into that ensembling techniques, I'm also going to walk you through the KNN coding part. Of course, in last session, we have discussed two algorithms, Naive and K nearest neighbor algorithm. With respect to Naive, we have even did the Python scripting with and without using the function from sklearn. But as for KNN, we have discussed only the math behind it, how the KNN algorithm works, how that nearest neighbor concept has been extended to classify the label information from the given data set. So that we have discussed in our last session, but of course we have not actually did the coding part. So in today's session, we are going to see that script part quickly. Then I will be moving towards the ensembling technique. So while I'm discussing the script part of KNN, the kind of data set that I have given to you people in our last session itself, it's having some kind of multi-class in it. So I have given one data set as plant.csv. So we are going to use the data set for K nearest neighbor model building. So what are the kind of extra challenges, or what are the kind of few modifications that we need to do while implementing the multi-class problem in sklearn? In that aspect also, we are going to do our discussion. And also, how should be the confusion matrix for multi-class problem, and how can we compute precision recall and all those things with respect to the multi-class? What is false negative and what is false positive with respect to multi-class? These things also quickly I will we will discuss before going into the ensembling techniques. So that is what the agenda for today's session. So we are going to discuss the scan and script part followed by ensembling techniques in detail. So I hope that everyone have that Jupyter notebook with you that I have shared during the at the end of last session itself. You have one PYNB file as KNN. So please open that KNN file. Let me share my screen. Please let me know everyone received this file from us, right?
Yes, sir. It is uploaded in Olympus.
Yes, great. So before going into this, of course, implementing this KNN is not something different from the way that we implemented decision tree or naive or logistic regression. So in sklearn, it's same, right? So the same kind of calling that from sklearn package, declaring that as an object, and fitting it and predicting it. So that steps is straightforward. We are not going to do any kind of changes really in it. All right. So, but anyway, before going into it, let me talk a little bit talk about that plant underscore CSV. So that plant underscore CSV, if you see, it's have some features, right? So 23 features. So I have named those features as F1, F2, F3, F4, so on up to 26, 23. So which means there are totally 24 features is there for this or exist in this data set, and there is only one target column. If you go and see in the target column, there are 4 levels in the target column. Target column 1, 2, 3, 4. But what is this feature? So let me quickly brief you that. So this features I have extracted from the image, right? So there are four classes, four folders. If you go and see inside each and every folder, there is some sort of image or plant image. So it takes some time in my system. Let me open this page. Right. So if you see, this is an kind of crop image, plant crop image. So this leaf or this crop has been diagnosed with some disease. Right. You can see some kind of gray shade, some kind of non-green pattern is exist in this leaf. That is an indicator of, or that is the sign of one disease. So now I'm just capturing this pattern. I'm just capturing this pattern exists in this image as some numbers, right? So whenever there is an image, and if you want to describe that image pattern, so or you want to extract some kind of features from that image, you can extract on the three platform. That image features you can extract as an shape feature, the image feature that you can extract as a texture feature, or that image characteristics you can extract as the color feature, right? So here maybe shape feature I can't use effectively. Shape is not a kind of feature which will be very discriminative for those abnormality exist in this particular image. So shape is the feature I can use while I'm defining the characteristics of the tumor from MRI image, tumor from some CT image, right? Because tumor is some kind of shape, right? Some tissue cluster. So the tissue cluster, whether that, what is the area of the tissue cluster, what is the perimeter of the tissue cluster, what is the circumference of the tissue cluster, whether it is smooth to circle shape or it is very coarse, something like that is meaningful to find. But here that abnormality here is nothing but the shade. You can see, no? So this shade, obviously you can't capture this shade or this pattern in terms of shape feature. So of course texture feature will be a helpful one, and color feature will be a helpful one, because we can clearly see this color of this abnormal portion is actually completely different from the normal portion, and also texture of the abnormal portion is different from the texture of the other normal portion. So obviously I have computed different texture based features and color based features for those images. So what is those features? Of course texture based texture features are nothing but the features that you can uh, compute through some kind of statistical equation, right? So mean is one texture feature, standard deviation is one texture feature, right? So like that any higher order moment, because how the variations of the pixels. So image is nothing but formation of the collection of pixels, right? So how that pixels are getting varied. So whether the pixel intensity is the same or that pixel intensity is different, you can see here this is the second abnormality. This is type 2 disease. So you can clearly see, previously I have shown you this image. So here that abnormality, this disease pattern is different, whereas here this abnormality or disease pattern is different. So we have to extract those features, or we have to characterize this pixel region which is actually forming that abnormal region, so that we can feed those numbers into our machine learning model, so that our machine learning model will understand or will capture the pattern of that abnormal portion. So that is what the idea. So I have just implemented some logic using image processing feature extraction concept. So let me quickly just share that script part. You can see here that I have just loaded the image and I have computed some features, right? So this I have done it in MATLAB. So straight away I can use some kind of functions through which I can easily found all those texture features, shape features, even color features, and so on. But anyway, even in Python, you have a package like OpenCV, you have a library called OpenCV Scikit image, through which you can effectively characterize the abnormal portion of the images. So that is what I have done with respect to this image. So now our discussion mostly in this course on structured data, not on the unstructured data. But anyway, this features that I have extracted from that images. I have written some code to extract the abnormal portions texture patterns, and these are all these numbers which is defining those texture patterns. Some of the texture pattern I have taken from some transform domain also. I have taken the frequency transform and wavelet transform of those images. Then on top of that transformed images, I have captured some of the features, right? So just to give an idea, like always, it is not that this kind of tabular data is available, right? So it is not like always we are doing only HR analytics, only some financial analytics where we have the customer data, where we have the product data, which is in a ready-made way available in a structural form. So sometimes we will be in the position to extract the structured data from some kind of unstructured data. So as I told, there are 4 different images, 4 different disease. That 4 different plant diseases. I have some images. So I'm just capturing or I am just extracting some numbers corresponding to those 4 disease type images. Then I'm just putting that in a structured way. So now this is like mean and standard deviation or even skewness, kurtosis, and homogeneity measures like entropy, some frequency domain measures like DC constant, wavelet measures. All those things I have computed for those leaf images or those plant images, and I have just arranged all those things in a structured way. So now what this means is the 0, 1 are the observations, which means that the plant portions. So how I did in the sense for the whole image, I have not taken only one feature. Say if it is if this is a whole image, what I have did in the sense I have done some kind of block processing. I have taken each block. So this whole image I have segmented. I have just blocked or I have cropped as 16 different regions. For 16 different regions, I have to I have just calculated all those 23 numbers. So like that, I have done some kind of image processing part, so that now I have got the structured image. Now once I have structured image, structured data, like 23 input features and one target feature, any machine learning model on top of it, I can easily apply so that I can build any classification algorithm. So that is what the idea. So here, after doing this, obviously the process is straightforward. I'm just taking that target column alone into one variable, and I have keep all other variable in my input column, and I am seeing that value counts all my representation. I have 4 class. Of course, this is a small data. We in order to improve the as we have a small data, the data set size is small. Obviously, that result also kind of on the lower side. Of course, we need to collect more data of the same disease so that we can increase the performance of this model. As of now, in this data set that I have collected, I have only just 30 rows to represent each disease, right? So for class 4, 30 observations, for class 3, 30 observation, class 2, 30 observation, class 1, only 30 observations. So with respect to that, so I'm just splitting this into train and test, and I'm just applying the k nearest neighbor classifier. So as I told, implementing the k nearest neighbor classifier is simple and straightforward. So this function k neighbors classifier is available under the library neighbors from sklearn. So we are loading that as from sklearn.neighbors import k neighbors classifier. So once I have loaded that, I am defining that as an object. So knn mod is an object, and in that object I'm just fitting my x train and y train, and I'm just predicting that with respect to my test data. So that is simple and straightforward as we do it for all the classification model. Then I'm just printing the classification report. So
Sir?
here we are. Sorry, any doubt?
Yeah, sir. Sir,
Yes.
this F1 from F1 to so on, it's all within abnormality, or it's all features, sir, of a plant?
No, this is like say I have taken for that whole region. Say for example, I have manually only did that segmentation process. Say even though this is a full image, I have taken only this part. Let me draw that. I have taken only this part. That is each and leaf part. Then I have just done a blocks like this. I have created the blocks like this. Right? So which means here all the region is having some kind of abnormality. All the region is having some kind of abnormality. Like that, the same process I have did for this leaf also. This is the another leaf. So for this leaf also, I have done the same processing. Like
Got it, sir. Thank you.
this region, and I have just taken the block. So it is not like I'm just doing the classification like normal and abnormal. It is for the 4 abnormal cases that I'm having like this. Between that 4 abnormal cases, I have computed this characteristic. So my model is now trained with respect to 4 abnormal cases, and it used to find which one is normal and which one is abnormal 1, which one is the abnormal 2, which one is the abnormal 3, and which one is the abnormal 4. Because the target class that we are having here in our data is not like out of this 4 cases, none of the cases actually normal. That one class is abnormal 1, 2 classes abnormal 2, 3 classes abnormal 3, and 4th class is abnormal 4. Right?
Yes, sir.
Yeah. Fine. So now, so you can see that in classification report, I'm just seeing the result for these 4 classes. Now, of course, we are seeing like the performances, overall performances around only 0.67. So especially that recall values for that class 1 and all little bit less. Of course, already the data is balanced, but of course I have only lesser representation. So there are 4 different classes. So I want to train my model to differentiate or find the pattern classes in the sense. So obviously I need to collect more images. So as this is a kind of real collection process. So I have images. Increase the number of images, and if we done the same computation for all those for more images, then obviously we can improve the performance of this model. But anyway, let us quickly discuss about the different challenges or some extra things that we need to do with respect to this multi-class problem. So here,
Sir, one
yes.
question. Can we parallelly run this code? Actually, I was running and in one of the cell I was getting error when we were appending in accuracy score.
So at the end, so you just make sure that whether we have declared the accuracy score.
Yeah, it is there. We were appending in that, so I'm not sure that. Okay, so actually it's not declared. I declared, but it should be as an array or something else.
No, it should be an array, no problem.
Okay, so I tried. Okay.
So I'm just running it up to this in my system also it is working fine.
Yeah.
Up to this matrix is working fine, right? Let me
Yeah,
run.
yeah.
So that if any error comes, we can see that too.
Sure. Yeah. Thanks.
Right? Fine. So now this is the confusion matrix. So obviously the confusion matrix is now having 4 rows and 4 columns. Typically, in previous session, the confusion matrix that we have discussed is had only 2 rows and 2 columns. Now I'm just having 4 rows and 4 columns. So how to interpret this? So if I ask you what is the false positive or what is the false negative, what could be your answer? If I simply asking what is false positive and what is false negative, what is your answer?
So we have to calculate for each class.
Exactly. So here that false positive and false negative, we have to compute for each class. Right? So that number of false positive and false negative is actually different for each and every class. Let me quickly show that how to do it. Let me copy paste this in Paint. So now, so this side is actually what this side of the confusion matrix represent? Actual side or predicted side?
Actual.
Actual. On this side is the
Predicted.
predicted side, right? So now say this is class 1, this is class 2, this is class 3, and this is class 4. Similarly here class 1, class 2, class 3, and class 4, right? So 4 classes. So rather than keeping 0, 1, 2, 3, just for the understanding, I have kept it as class 1, class 2, class 3, class 4. Now with respect to class 1, so with respect to this class 1, this number determines the true negative, true positive with respect to the class 1. So how many class 1s are correctly identified as class 1, right? So what this number representing? What this number is representing? What this number is representing?
False class 1.
So how many actual class 1s are wrongly predicted as class 2? That is what this number, right? So now whether you are going to count this as false positive or false negative.
It should be false negative.
False positive.
It's false negative. In other, so it is like how many actual class 1 has been wrongly classified as class 2, which means now I'm just making all the statement with respect to class 1, which means class 1 is my positive case, right? Because whether it is class 1 or not, that's how I'm saying. So what I'm focusing, that generally we will be considering as class 1. If I'm just finding whether cancer is there, I will consider cancer as positive. Whether the employee leave or not, if whether the employee leaving attribute is the main thing for me, then I will be considering the employee leaving case as a positive case. So like that, what I want to focus, generally people will consider that as a positive. Here, respect to class 1, now so class 1, I'm just considering as positive. So how many class 1s are correctly identified as class 1, which is nothing but TP. So with respect to class 1, TP is equal to 4. Then how many class 1s are actually wrongly classified as class 2? So if something has been classified as class 2, then class 2 is in my negative case. Class 1 is positive, all classes are negative for me with respect to class 1. So falsely, how many identified as class 2, which means falsely, how many are identified as the negative class, which is something but false negative. So here, totally, how many false negative?
5.
So this is also false negative for me. This is also false negative. This is also false negative, because while I'm analyzing class 1, if it is not class 1, all other things, all other classes, whether it's class 2, class 3, or class 4, is a negative class for me, right? So false negative here is 0 plus 1 plus 4. This is false negative with respect to class 2. This is false negative with respect to class 3, and this is the false negative with respect to the class 4. So the total false negative for this model is 5. The total false negative for this model for this class 1 is 5. Similarly, what's about the false positive? What about the false positive?
2.
Only 2. So this part, right? So these 2 are false positive, because actually it has been predicted as positive. So see, this is predicted here. The predicted is C1. My model is predicted as C1, but if I see the actual case, the actual cases are C2 and C3. Actually, these 2 observations belongs to class 2 and class 3, but my model predicted that as class 1. So as class 1 is my positive case, now in this analysis, as it is wrongly predicted as class 1, it is known as false positive. So here it is 1 plus 1 plus 0. So this is with respect to C2, this is with respect to C3, and this is with respect to C3. So my false positive is actually 2. My false positive is actually 2. All right. So what is mean by true negative then?
20.
So which element? So this is actually false positive.
Diagonals.
False positive. Which one we will be considering as true negative for this case? All other.
Diagonals. Yeah.
All other.
These are all actually true negative. Because the my objective is to check whether it's class 1. Of course, this is actually saying that this is actually class 2, and my model is also telling us class 2. This is class 3, my model is also telling us class 3. This is class 4, my model is also telling this is class 4. So these are all the true negatives. These are all the true negatives. So like that we have to calculate or like that we have to see this false positive and false negative for each and every class. For each and every class, so that now if I'm finding the recall or sensitivity, then TP divided by TP plus Fn, then I have to use this TP as 4 divided by TP plus Fn 4 plus 5. So like that, that corresponding numbers I have to use for finding the recall precision for that respective classes. So similarly, you can write, from the confusion matrix, you can understand which one is the true positive and which one is the false positive and which one is the false negative for the class 2. Similarly for class 3 and class 4. So this is how you need to understand the confusion matrix of multi-class. Confusion matrix of multi-class. Got the point? Any doubt in it? Yes or no?
True negative. Why is it only diagonal against the C1?
Yeah, it's against C1. See, this is say these are all with respect to the class 1. With respect to class 1, what are all the negative classes? As I told. Say I'm just class 1 is positive. If I consider class 1 is positive, what are the classes which are negative?
The remaining ones.
The remaining ones. So C2, C3, C4 are the negative classes. Now in my model is actually identifying 7 C2 classes correctly as C2, right?
Correct. Oh, okay. Okay. Understood.
So which means it's true negative.
Okay. Got it. Okay.
Right.
So one confirmation here.
Yeah.
So the true negative for C2 class would be the other diagonal elements, as in the 4, 5, and 8, right?
Yes.
Okay. Thank you.
And so for C1, except for the other diagonal value, right?
For
C1?
For C1?
7, 5, 8?
Yes, 7, 5, 8 are true negatives.
Okay.
I have marked to know because my objective is finding all those numbers with respect to C1. So C1 has been correctly identified as C1 means then it is actually true negative, true positive. All other classes correct identification. C2 correctly identified as C2, C3 correctly identified as C3, and C4 correctly identified as C4 are true negatives because with respect to C1, all other classes are negative classes for me. So C2, C3, C4 correct identifications are true negatives. Similarly, if I'm finding with respect to C2, all those numbers with respect to class 2 that I'm finding in the sense, then 7 is my true positive. This 4, 5, and 8 are my true negatives. Got the point? Yes or no?
Yes, sir.
Yeah.
Sir, I have one query actually.
Yes.
With respect to the structure of this confusion matrix. So here we have taken the predicted on the top and the actual to be on the left side, right?
Yes.
So we can take either way, right? We can take even predicted on the left side and actual on the top.
So if you are actually from your y pred and y actual, you are actually constructing the confusion matrix with pen and paper. You can do it in any way that you want, but sklearn will always give in this way. Whatever the confusion matrix which is given in the sklearn, so this side is actual and this side is predicted. If you consider once you are taking the confusion matrix from sklearn, you should not consider this top side as actual. Then that is wrong.
Yeah, that was a mistake I did actually. I mean, for the last week's quiz, right? It has given a confusion matrix and asked us to
Yes.
compute the precision. So I was confused because in deck it is given as Pareto values on the left side, confusion matrix. So okay, so as per the scale right? Okay,
Yes.
so okay.
Actually, in R, it is ulta. I think I have mentioned this point while I'm reducing the confusion matrix. So in R, say if you are running this some code in R programming, and if you are seeing the confusion matrix, in R, the top side is actual and this side is predicted. So we have to be specific. So which side is predicted, which side is actual with respect to that tool. With respect to that only, we need to make we need to compute precision recall and all those things.
Okay, thank you.
So this is about how to infer in the multi-class confusion matrix. Now let us move into this code part. Now I'm just trying to plot the ROC curve for this multi-class. So I'm just running this. You can easily plot the ROC curve for the multi-class if you are using the if you install this package Scikit plot. So there is one package called Scikit plot. So you can install the Scikit plot so that you can quickly easily plot the multi ROC curve. But here, before going into that, what is this table telling to us? Can anyone tell? What this table is telling to us? Why prob?
Probability of each class.
Probability of each class. Right. So the first observation is belongs to which class? Can anyone tell? By seeing the
C3.
it belongs
Class 1.
to class
C3, right? Class 3.
Yeah. So each and every row is having the corresponding class probability of that first observation. So this is the first observation. So first observation means, so this is our first data, right? F1 to F3, it is having a number like this. What is this corresponding class probability? That I can see it here. If I give only predict, it will give just 1 or 2 or 3 or 4. If I give predict proba, what is the probability for each and every class it will give? So the first column talks about the class 1 probability. The second column talks about the class 2 probability. The third column talks about the class 3 probability, and the fourth column talks about the class 4 probability. So this first row numbers in prop table, the first row numbers talks about the 4 class probability of that first observation. So out of those 4 numbers, the third number is high, which means third column is having the high probability, which means that particular observation is belongs to class 3. Right? Everyone got this point? I heard someone told class 1. Now you got the point, right? Yes or no?
Sir, can you repeat once again?
See, what is the what is the class probability of one particular observation that has been given by this each and every row in this probability table, right? I have just shown you only the 10 numbers. If you want
Yeah.
see for the 10 numbers also, or 20, whatever, for all the observations also you can see. Now the first row, what it is actually telling us, in the first row, this first number 0.2 is telling us there is only 20% probability that this observation is belongs to class 1. And the second number is telling that there is 0 probability that this particular observation belongs to class 2. The third number is telling that there is 60% probability that it belongs to class 3. And the fourth number is telling that there is 20% probability that it belongs to class 4. So as 60% so with respect to this observation, my model is telling with 60% confidence that it belongs to the class 3. So we are making the decision like this particular observation is belongs to class 3. Got the point?
Yeah.
Yeah. So now so we need this threshold values, or we need this probability values to plot the confusion matrix. But the problem is that that ROC plot that we have used from sklearn will actually work only for the binary class. It won't work for the multi-class. So we have to do other lot of changes in order to make that work for multi-class, but rather than that, simply use the scikit plot. So using the scikit plot,
So one quick question. On the last row in the observation, 0.2, 0.4, 0.4, and 0,
yes,
will it take class 2 or class 3? Or we go with that last time you mentioned about the weighted,
yeah.
or
It is actually go with, let us check, white test.
It will check for 2 or 3 decimal points, sir. I think based on that, because the only one showing.
Actually, it's taking class 2. It's taking class 2. But generally what happen if there is a tie happen in terms of probability weightage or in terms of neighbors, something like that. If tie happens, what it will do is it will actually see your class distribution. It will actually see your class distribution. So between these two classes, which class count is actually more? If class 2 count is more than class 3, then it will give us class 2. If class 3 count is more than class 2, then it will declare as class 3, right? But here in this case, even classes are same. If you see here, all the classes are 30, 30, 30, right?
yeah.
So which means it is actually taking the first occurrence, something like that. So class 1, class 2, class 3, class 4, no? So it's just nothing but we have not named as 0, 1, 2, 3 or 1, 2, 3, 4. So maybe it is actually taking that in that alphabet way or that numeric and numbering way, right? So generally if tie happens, it will go and see the class count. So as class count is also same, I think most probably it will go with an alphabet or just go with that number range. So for that say like our one not encoding, the other techniques actually do that labeling with respect to if you have an levels like from A to Z, it will give priority to A, right? So whatever the string which starts with A, for that it will name as 1. Whatever the letter will start with C, then which is the next level, means the next number only will be assigned to C. So like that, it may go with that ASCII range or that number level range. So in this case, it is actually assigning us 2. It is not actually assigning us 3. So which means it's going with that ASCII number pattern. But generally, it will go with class count. As class count is same, it's going with that ASCII number pattern. Got the point?
Yeah. Thanks.
Because here there is no concept of weightage. In KNN, we have discussed something called weightage, right? If you give weighted, then it will go with that concept. But here it is simple probability. There we have used to find the distances, which distance is more, which distance is less. Based on that weight concept is available only for KNN. Here there is no weight concept. But irrespective of whatever the algorithm, if tie happen, it will go generally by seeing the frequency count of the class. If frequency count of the class is also same, then obviously it will go with the ASCII pattern.
Sure, sir. Because the count is both 30, 30. That's why I was checking.
So this is the syntax to plot the multi-class plot. So the function is from sklearn, you have matrix. From that matrix, you have plot ROC. This is not sklearn matrix. It is scikit plot matrix. From scikit plot matrix, we are using the plot ROC. For that, we are giving the y test and y prob. So this sk plot matrix will support even this y prob is having the multiple columns. But your sklearn won't support if this y prob is having multiple columns. So which means your y prob won't, your sklearn plot ROC won't support your multiple class. That is the reason why I'm just using some other function from other library. So plot micro equal to flux. It used to give that micro plot, macro plot, weighted average plot, and all those things. We don't want all those things. So that micro plot, I'm just making that as false. Plot macro is also false. I want just a typical ROC curve only. If you want how it is plotting plot micro and plot macro, you just go to the go and explore the documentation page of this scikit plot ROC. Now by giving all other argument as false, I'm just seeing the typical ROC curve. I'm just seeing the typical ROC curve. So the ROC curve for class 1 is 0.76, ROC curve for class 2 is 0.84, ROC curve for class 3 is 0.88, and ROC curve for class 4 is 0.85. So with respect to the ROC curve, my model is fine. It is not like anything, none of the model is actually close to 0.5 or less than 0.5, which is the severe issue. But it is actually well deviated from that coin toss model. That is that dotted line, which is the poor model. So my models are well above that poor model. So simply whenever you are in the position to plot the multiple ROC, multi-class ROC curves, so you can use this Scikit plot. But anyway, the concepts are all remain same. So for this is a graph between the true positive rate and false positive rate. The only thing is the true positive rate and false positive rate, how you need to compute, you have to use the appropriate formula for true positive rate. True positive rate is TP divided by TP plus Fn. So you need to know what is TP and what is Fn for each and every class. Now we have discussed that with respect to the confusion matrix, how to find the TP, Tn, Fp, Fn for each and every class. Once you know that, you can calculate what is TP and what is Tn. So obviously this computation need to be happen for different thresholds, right? That sklearn confusion matrix is only for 0.5 threshold, but here this function will actually compute this TP, Tn, Fp, Fn for each and every class by constructing multiple confusion matrix that it is derived by keeping different thresholds. So with respect to that, it is getting multiple points for true positive rate and false positive rate. By connecting all those things, it is actually plotting the curve. So this is same as that of the confusion matrix and ROC curve that we have discussed for the binary class. Here the only thing is, as there is a multi-class, the TP, Tn, Fn values will differ for each and every class. So that is the reason here we have to compute it separately and we have to plot this. But anyway, if you are using this package from Scikit plot, it automatically do all this computation internally and it will give you the graph. So this is how you need to plot it. Then one another cool thing with respect to this KNN nearest neighbor is, I say here what I'm doing, I'm just taking only one sample. So in the X test, I'm just taking the first row alone, right? So this first row alone, I'm just passing as one input. So because whenever, so what is this reshape of 1, -1? Why I'm deliberately doing this? My objective is just pass one row into my model.
Yeah.
Why I'm doing this dot values dot reshape of 1, -1?
Not removing the last column, right? The target one.
No.
No, get the whole rows for.
Yes. Say if I just, I'm just inserting one cell. If I run this, by default, if you access only one row, even though this F1, F2, F3, F4 are one row, your Python data frame or a pandas data frame, it just consider as one series, which means it's only one column of data. Only one column of data. So this is now one column of data, right? If you are, even though I have taken the first row, now that first row has been depicted in one column of data. I don't want this to be a column. I want this to be a row. So I can resize this as row. For that, I can use this reshape function, but reshape function will work only for array. So I'm just using as values so that momentarily it will convert that into array. Then I'm just using the reshape. So reshape, you can give how many rows and how many columns that you want here. The first element is on rows and the second element is columns. Rather than that, whenever you are in the position to redistribute into complete one row, you can simply give us 1, -1. So whatever the data, if you give that, say even a 64 × 64 big matrix is there. If you just take that and if you give reshape of 1, -1, all that 64 rows and columns of number will redistributed into just one row. Similarly, if you give -1, 1, it will be redistributed into one column. So that is the idea here. So now I have just kept it only one row and I'm just passing just one row here, because in a column format, if I pass, it will throw you an error, because your model has been trained such that it will accept the input as an rows, right? But here, if you take only one row, by default, your data frame is making that as a series so that it will become a column. So you can't pass one column as an input to your model. That is the reason I'm just reshaping that. So once I pass this, I'm just getting, this is my trained model, KNN mod. I'm just using the method K neighbors. I'm just using the method K neighbors and K neighbors of just one sample. Now it is actually giving me the two array of information. The first array of information talks about, the first row of information is information is talking about the distances. The second one is actually talking about that corresponding neighbor index, neighbor row index. So by seeing this, I can tell, like, with respect to this first observation that I have passed as test, 0th index observation that I have passed as test, the 9th observation is the closest neighbor. The 9th observation is the closest neighbor, and 79th observation is the next closest neighbor, and 30th observation is the next closest neighbor, and 4th observation is the next closest neighbor, and the third observation is the 5th closest neighbor. And these values are talking about the distances. I'm telling, like, the 9th observation is the immediate neighbor, but what is the distance between? What is the distance between that neighbor and my test sample? 2.4 is the equivalent distance between that neighbor and the test sample, whereas 3.15 is the distance between the second nearest neighbor and the test sample, and 3.67 is the distance between the third nearest neighbor and the test sample, and so on. Got the point? What your K neighbors is telling to you? Can you think of some application with respect to this K neighbors? Can you think of some application with respect to the K neighbors?
Shopping cart.
Exactly. So in e-shopping and other domains, say I have the user. Say each and every row in my data is some user characteristics. User characteristics, like what is the user age and how many movies that he watched, what is the genre of the movie that he is watching, and what is the kind of rating that he is giving for each and every movies. So like that, each and in my data set, each and every row talks about the characteristics of the user. Characteristics means its personal characteristics, its demographic details, and also its usage details, how he is using the Netflix, how he is using the YouTube, what are all the what is his watching pattern. So like that, this information has been captured for each and every user. Then I'm just building some kind of KNN model to predict whether what kind of genre he is generally watching. Say the target column could be a genre or whatever. But now, even though whatever the target column, whether he is an frequent user or a frequent watcher who is a loyal customer, something like that I'm predicting. But anyway, forget about the predicting, whatever could be the target column. Once I have built the K nearest neighbor model with respect to this user data, if I do the model dot neighbors of any one user data, here the test data is nothing but any one new user data. Say one new user has been registered in my website, or there is one user who is there in my portal. I'm just using that user data here using the method K neighbors. What it will give to me? What it will give to me? With respect to this domain context, can you tell me? The data that I'm having is the user characteristics. Each and every observation in my data is having some user characteristics. So now I have built some K nearest neighbor model, and after that KNN mod dot K neighbors of one user detail only I'm just passing here. What it will give to me?
Yeah, user 9 will be closest user.
Yes. So say this is one user. Say this is me. This test is me. It's my data, and my algorithm is now telling me that user 9 and 79 and user 30, user 4 and user 3 are my closest neighbors, or my closest 5 neighbors. So what Netflix will do, what YouTube will do, actually what is the characteristics of this ninth person? It will go and check, and what are the movies that he watched is go and check, and it will just cross verify that, say user 9 actually watched, say 5 movies. Out of that 5 movies, I have also watched the 3 movies, right? Then the other 2 movies is there, no, as he is the closest neighbor to me, Netflix assume like, or make a decision like, as he is the closest neighbor, my watching pattern and my neighbor watching pattern may be the same. So what it will do is whatever the other 2 movies that user 9 watched, but I yet to watch, it will recommend to me. It will recommend to me so that it will make that recommendation more sensible. Are you getting my point?
So in this particular example, how do we visualize, like, because we have F1, F2, F3 as multiple
Here,
features.
yeah, of course. Here I'm not. Here it is actually classification point of view only. So here say here one kind of rough idea is, say, with respect to this test sample, 0 sample. So these are all the kind of closest sample. If I go and see this out of this 5 closest sample, many of them have the same kind of disease. So like that only I can interpret. So what my point is, you can extend this neighbor concept, even though it's a classification is our objective, you can extend this to do some kind of recommendations also. But here there is no point in doing recommendation with the plant disease case. So here what it is telling, these are all the 5 neighbors. If you go and see that F1 and F26 values, this F1 to F26 values are kind of close to this test sample. Say if I'm having some kind of entropy value, that entropy value of sample 9 is actually having kind of close value with respect to the entropy value of my test sample. So like that, I can get some kind of idea, but that is actually meaningless. Here there is no kind of recommendation that I'm going to do. So it is a kind of distance we are computing based upon the distance, whether this particular sample is belongs to disease 1 or disease 2, disease 3 or disease 4. That classification decision that I'm making, that is fine. But what I'm telling is, using this k neighbors, you can also extend this algorithm to make some kind of recommendations.
Okay. And the second row, which talks about the index, is in the whole row.
Yes, this is the index of that whole row. This is the 9th sample. 9th sample now in this case is having 23 numbers.
Got it.
If you see the 23 number, what is the 23 or 26 numbers of 9th sample, how much distance it is having with respect to this test sample, that has been given by this number 2.46. Got the point?
Yes, sir.
So likewise, k nearest that is neighbor logic is one of the logic popularly people is using in recommendation system also. Still, many recommendation engines are actually using this neighbor concepts, right? So what are the similar items? What are the similar product? What are the similar uses, right? So of course there are so many other concepts also there in recommendation system, but a basic recommendation system we can also build using the nearest neighbor concept. So after this, of course, I'm just doing this cross-val score. But here, that one point that I want to stress you is, I want to give focus is, say here I'm just using something called make scorer. Right. So typically, what we will do, we will run like this, right? So scoring, I'm just using as F2. So generally, I will run like this. From sklearn dot model selection cross-val score k-fold, all those things I'm just giving, and CV equal to 5, scoring equal to F2, and I will run. So if I run like this, it will throw me an error. It will throw me an error because for multi-class problem, the only scoring function that you can use by default is accuracy score. Because do you think that accuracy will be computed for each and every class separately? Here in this table, accuracy is only one for that whole model. Out of total classification, how many classifications are correct? That's it. How many total, out of total observations, how many are correctly classified, how many are wrongly classified? So we are not actually going to calculate the accuracy for each and every class, right? If you calculate each and every class, then it will become recall. And also you can compute precision, something like that. But for overall model, if you are calculating the accuracy, how many class 1, class 1, that is all the TPs on the TPs and TNs are on the numerator, divided by, which means in other words, with respect to the confusion matrix, that accuracy score of your whole model is sum of all the diagonal divided by sum of all the numbers. That's it. That is only one accuracy score. Sum of all the diagonal, because all the diagonal numbers are correct prediction. All the non-diagonal numbers are wrong predictions. So correct predictions divided by wrong predictions. All the diagonal sum of all the diagonal numbers divided by sum of all the non-diagonal numbers or non-diagonal elements are nothing but your accuracy score. For one model, there is only one accuracy score, even though it's a multi-class. So your cross-val score work well if you use, in place of scoring, if you use accuracy score, right? But if you use anything like F2, if you use anything like precision recall, then precision recall and all need to be calculated for each and every class separately if you are using the multi-class, right? So if your data is having a multi-class in its target column, so obviously through just passing F2 will throw you an error. So we have to, sorry, not F2, F1. Even F1 will throw you an error. So if you give precision, if you give recall, everything will throw you an error. So we can't actually train our model, or we can't actually compute the overfitting nature of the model with respect to the other measures apart from accuracy score if it is a multi-class, if we are using the scoring function as it is. So we have to do some kind of modification. What is the modification we have to do? There is one another option called make scorer. So we have to define that. So that function is there in matrix. So from matrix, I'm just loading F1 score. F1 score we know individually, separately. I want to find F1 score, I have to use F1 underscore score. Recall, if I want to find separately, I have to use recall underscore score. So like that, I'm just loading F1 score separately, and also make scorer method, I'm just loading it. Then I'm just using defining that make scorer separately, make scorer of F1 score, comma, average equal to macro. So of course you can give average equal to macro or average equal to weighted. So we already discussed with respect to the confusion matrix. Macro is the simple average of for each and every class you will be getting one F1 score. Just average of all those class F1 score is nothing but the macro average. If you give weighted average, how many samples has been used to make the decision, that also will be taken into an account while finding the average of the 4 class F1 score. So here I'm simply using the average equal to macro. Then in place of the scoring, you have to give scorer, whatever the name that in which you have defined your make scorer. So that you need to give it here, so that now it will work perfectly. And we are getting that 0.52, 0.47, 0.39, 0.53, and 0.51. Of course, I can see a clear kind of overfitting because there is not enough data is there for my model to learn. So obviously we will be expecting some kind of overfitting, because you can see F1 score is as low as 0.39 for some iteration or for some split, and for the other split it has been as high as 0.53. So if you see the range, it is a little bit high. So even if you compute your mean value of all those things, even though it comes somewhere close to 0.47, something like that, definitely CVV will be getting a little bit high. So this is the one small modification you need to do while you are applying CV concept. This is not only for cross-val score. So if you are using grid search CV is also internally use this cross-val score, right? Because whatever the trained data that we will give, it will split and it will just work on it. And also your grid search CV is also needs scoring function. So you need to give scoring function. So whenever you are dealing with multi-class problem and you are actually optimizing your model with respect to some scoring function, so that scoring function you have to, or that scoring method you have to create through the make scorer option for a multi-class problem. So this one extra point you have to keep in your mind whenever you are dealing with multi-class, right? Then obviously I'm just running this as usual as we did in our yesterday session in our last session. We have actually implemented this tuning in two ways. One is simply by using the for loop, how to tune one or two parameters alone, and then later on how to use the grid search CV to tune my whole model with all the parameters. So that is what the idea. So here why I have deliberately using the for loop to tune it, I told like research CV is ultimately takes a lot of time. That is one factor. The another factor is research CV will make the decision with respect to the buyer's score. That is the average of those 5 splits. Based on that only it will take the decision. But sometimes you will be in the position to take with a decision with respect to the variance scores. So you can also do that using research CV by seeing that standard deviation column rather than making decision with respect to your mean average column. But anyway, it takes some time if you tune all the parameters in one go. So sometimes it is even healthy to tune the parameter individually, provided that that particular parameter don't have any kind of impact on how that other values of other parameters. So in that case, you can tune that particular parameter individually also. So here I have done individually, I have tuned with respect to the neighbor n equal to k. Here I am just plotting with respect to the accuracy score. So I think in my initially in the script that I have shared with you, I have not actually declared the accuracy score. That is the reason you may get error. So here, if you see metrics, I have imported no F1 score. In that case itself, I'm just loading the accuracy score also, so that I hope you won't get any error and you can run this. And I'm just plotting it. For train and test. Right, so I'm just computing for different k values. For different, last class itself we have discussed the hyperparameters for k nearest neighbors are number of neighbors and distance metrics, and in what way it need to make the decision by ensembling or by seeing the n number of neighbors, whether it need to take weighted way or uniform way. So these are the 3 hyperparameters with respect to the k nearest neighbor. Here I'm just tuning with respect to only n neighbors, and I'm just plotting it train performance and the test performance. I'm predicting with respect to x test and predicting with respect to x train also. So I can see here, of course, the train performance and the test performance deviation, at what point it is less, I have to see. So this blue line is for train and orange line is for test. All right, so here you can see in what place I have to give us the accuracy score. We are not actually doing this with error. We are doing with respect to the accuracy score. So I want that value to be little bit on the higher side. So this point even I can take. When k equal to 5, and that accuracy scores are kind of higher side, because around 0.7, here also it is 0.68, and also you can see the gap between this blue line and orange line is actually kind of less here. Even here, if you see, the gap is actually almost same or kind of less, but still the overall performance is less. I want, as is an accuracy score, I want that accuracy to be high, but at the same time, I want the accuracy to be high, but at the same time, I want the gap between the accuracy score of train and test also to be less. So I can choose k equal to 5, or even k equal to 3 is reasonably doing well. Yes or no?
Can we not take 8? It is at the same point.
Yeah, you can take 8, but the thing is almost both are same, but overall the performance is a little bit down, right? It is only around 0.62, something like that. Yes or no?
Okay, and what is the y-axis? With
Y-axis
the probability.
No, just simply an accuracy score.
Okay.
Accuracy, say it is almost our accuracy is, most of the accuracies is in around 60 to 70%, right? So y-axis is the accuracy score, and x-axis is the number of neighbors. As he telling in 8, almost both the scores are same. At this point, it's coming somewhere here, then I will be really happy to have 8 as a nearest neighbor, right? But here it is actually train score and test scores are same, but this is on the lower side. So of course, if it is fine in your domain, say achieving this accuracy is fine, then you can go with this. But I can even go with k equal to 3. The gap is not that much between this blue line and orange line, and also the overall performance is on the higher side. So Likewise, you can see the plot and you can also make the decision. Right? Then again, of course, I'm just using the grid search CV by applying all those things. But again, you can see here in grid search CV, I'm just using the params as an n neighbors. Metric, I'm just using only Minkowski. Because with respect to Minkowski, if I vary the value of P, then it's become different distances. Minkowski with P equal to 1 is what distance? Can anyone recollect our discussion?
Manhattan.
Manhattan. So it's Euclidean with P equal to 3. Of course, it's become some kind of higher order distances. So, and also weights we are doing with uniform and distance. So these are the only parameters, conceptual parameters. There are some other parameters as n jobs equal to -1, which will be using all your resources, and also some algorithm like brute. Some algorithms are there, but that algorithms are, we are not actually discussing those algorithms in the explanation of the classification. These algorithms will effectively, that K-tree, brute, all those algorithms are actually for optimization. How effectively it can work in a way so that that result can be obtained in a quick way. So in that sense, you can also vary few other parameters. So here scorer equal to again make scorer. Why I'm just using make scorer? Because grid search CV is using the scoring as one option. Whenever you have scoring as one method, so obviously you have to use this make scorer function in order to define that scoring for a multi-class problem. If you just use any one single number, it won't work. It will throw you an error. But of course, accuracy score you can use even for a multi-class problem. Scoring equal to accuracy score you can use. But if you use any other parameter apart from accuracy score for a scoring, it will throw an error for a multi-class problem, because as multi-class, you need to instruct it in what way it need to find that F1 score or recall, because as this is having a multiple class, whether you need to find it in a macro average or a weighted average. So that we have to define separately, then only it will work. So with respect to that, I have constructed this. Once we have run this, we are getting the best parameters. Suppose it takes some time, because each and every test sample need to be compared for all those different parameters. Then obviously we are getting like n neighbors equal to 3. It is giving us the good performance, right? Here also we have seen that, right? Because as we know, grid search CV is actually making the addition with respect to the only buyer score. It is coming like this. If it is also taken the variance into our account, maybe 8 could be the better choice. But anyway, with respect to the grid search CV, we are getting the these are all the parameters. Matrix is Minkowski, and P value is actually taking us 1. With respect to this data, P equal to 1 is actually doing well compared to your P equal to 2, that is Euclidean distance, and n neighbors is taking us 3, and weighted also it actually taken us uniform, because by applying different weights like weight equal to uniform and weight equal to weighted, it has come to know that uniform is giving the better results. So that what is that better result? That better result is this best. So these are all the things that we have already discussed with respect to decision tree. Also, even in our linear regression model, we have discussed how to interpret or how to do with grid search CV. But anyway, just for the sake of completeness, I have demonstrated all those things here also for the k nearest neighbor. So the focus will be on the script is on how to do some kind of changes with respect to the multi-class. So what are all the places in syntax you have to change the appropriate modification, so that you can run the or you can print all those values even for a multi-class data set, right? So this is what I want to share with you with respect to the k nearest neighbor algorithm. Any doubt in this multi-class part or in this coding part?
I have one doubt. So here the best score, when it says that is accuracy score or F1 score, is it?
Is it F1 score?
Okay. Yeah. And second doubt is the one in the ROC curves, right? We have a plot on the top.
Yes.
So here, so for the class 4, no, for the class 3, it has the highest area.
Hmm.
So, I mean, what does that signify actually? What does it tell us? That area 0.88.
See, say what it tells us, if you ask that, say that area is actually proportional to, or that area talks about how effectively your model actually identifying your true positive cases without allowing false positive case to happen. So generally what happened, the true positive cases will increase provided that your false positive cases also increase. Say if you are keep on increasing your false positive cases, definitely your true positive cases also going to increase. But I don't want such a kind of model. I want my model to detect all my true positive cases correctly without allowing or without declaring anything as false positive. So if the area is more, then it means that with less false positive, all the true positives are correctly detected. So which means in class 3, the true positive, the model's ability to identify the true positives in class 3 without allowing the false positive is actually more.
Okay. Thank you, sir.
Right. Fine. So
Just one doubt.
yeah,
Could you please go back to confusion matrix?
this one
So yeah, below that one matrix is there, no sir?
below that.
Below that, little scroll below. Yeah, here, what does this third row, fourth row and all interprets? Could you please explain? I didn't get that.
The first row you understood?
Yeah, first row says that class 3 is highest
IS for which observation?
for
See, in my data there are 10 observations.
yeah.
Right. So just imagine like this is the 10 plant, right, or 10 leaves that I am having. For the 10 leaves, I am just computing some kind of features. So now I have the features for the 10 leaves, right? So now that first row, it's talking about that first observation in my data set. In that first observation is belongs to which class? By seeing
Third
this
class.
4 number, I will take that the first observation is belongs to the third class. Similarly, in my data set, second observation is there. No, the second observation is belongs to which class? The second observation is belongs to class 2 because the class 2 column is having the highest probability. Then the third row talks about the third observation is belongs to which class?
Class
The
1.
third observation is belongs to first class.
So the highest is taken. Yeah, fourth one is belongs to class 4.
Yes, fourth observation in my data is belongs to class 4.
Okay, got it, sir.
Yeah.
Thank you.
Thank you. Right, fine. So this is about that workout. Obviously, I have shared it. That is the reason why I have just walked you through this code rather than typing and doing it. So now, with this discussion, let me go to the next algorithm. Fine. So now we are going to discuss one of the popular algorithm in machine learning world, which is known as random forest. It is known as random forest. So our discussion throughout this day, most of the time in our remaining session, we are going to spend on understanding this random forest. Of course, implementation again, it's very simple and straightforward. So we are going to spend more time on understanding this algorithm, random forest. Say we have already discussed decision tree. Obviously, we are going to extend the concept of decision tree to understand this random forest. To understand the random forest, if we understand these two terms, what is random and what is forest, that itself actually give you the clear idea of how random forest works. So basically we need to understand these two terminologies, random and forest. First we will discuss what does this forest mean. So generally what is forest? Generally what is forest?
Collection.
Collection of trees.
Exactly. So from the tree, with the tree, if I ask you to just define the forest in the general sense, forest is having multiple trees, lot of trees, right? So forest is having collection of trees. So we have already discussed decision tree. So we are going to extend that concept of decision tree to the random forest. So which means what does the forest mean in this term random forest is? It's a collection of trees. It's a collection of trees, which means in random forest algorithm, we are going to construct multiple trees. We are going to construct multiple trees. Decision tree algorithm, for that whole data set, we have constructed only one tree. With respect to that one tree, we have made our decision for that input test sample. But here in random forest, for that one single data set, we are going to construct the multiple trees, multiple decision tree. The same way, the way that we have constructed decision tree, that max concept, that Gini concept, entropy, all those things remain same. Max depth, what is max depth, what is minimum sample split, what is the minimum sample leaf, all the concepts, what is pruning, everything remains same, right? So, but the only thing is, we are not actually going to make the decision with respect to only one decision tree. We are going to construct multiple decision tree. So that is the name. That is the reason why it is actually named after forest. Then the next term here is random. So random, which actually gives the answer for how we are going to construct multiple trees. How we are going to construct the multiple trees? So the answer for this question lies in this concept of random. So forest means collection of trees, which means we are going to construct many trees in random forest. But how we are going to construct multiple trees with respect to one single data set? So if I have only one single data set, with respect to that one single data set, I will construct only one tree, one decision tree. How it is possible for me to construct multiple decision tree? For that only we are going to use this concept of randomness, right? Let me explain that. Say our data set size is say 100 cross 12, which means we have 100 rows and 12 columns. So with this, typically you can form one decision tree. Everybody know how to construct one decision tree for this 100 cross 12 columns. Can we quickly refresh how we say if 100 cross 12 data set is given to you? How will you construct a decision tree? Can anyone just tell what is the first step in constructing the decision tree? Once you have a data set in your hand, sorry, your voice is breaking.
Impurity.
Sorry.
Find the Gini impurity for the root.
Exactly. Find the Gini impurity for all the 12 input features. Say this is an input feature, right? With the output feature, that data set size is 13. So I'm just talking about only the input features here. So 100 cross 12 input feature, and of course one output feature. That is one output column. Say if I have 12 input column, for the 12 input column, I have to find the Gini, and I will be saying that for which column the Gini impurity is less. Right. So then if say if I identified for the fifth column the Gini impurity is less, then the fifth column I'm just going to use as a main root node. So using that, I'm just going to split my data. Then some of the out of this 100 data, say 60 data is going on the left side node, left side of the for the left child, and 40 40 observations are going to the right child. Then with respect to that 60 data, once again I have to compute all the Gini impurities for all the columns. Then I have make a decision about how to split that 60 observation further. So like that I will keep on do until all the nodes are become pure, or with respect to the overfitting nature of the model, I will stop at any point. So that is what the idea of constructing the decision tree. So obviously if I do this process, I will be able to construct only one decision tree. But now here I'm in the position to construct multiple decision tree. So I'm going to construct the multiple decision tree. So what I'm going to do is, rather than taking all the 100 data, rather than taking all the 100 observation, I'm just going to take, I'm just going to take only say 60. I'm just going to take only 60 observation. So 16 cross 12. So all the input column, but I'm just going to take only the 60. I'm not going to take all the 100 observation. So now with respect to this 60 observation alone, I can construct one decision tree. So everyone agreeing that the same way, the way that we are going to construct the decision tree is going to remain same. But rather than using all the data, rather than using all the 100 data, now I'm going to use only the 60 data, 60 observation. With respect to the 60 observation, I'm just constructing one decision tree, say DT1. Now, say if I say with respect to the 60 data, I'm constructing one decision tree. Like that, how many decision trees that I can construct by using 60, 60, 60? How many 60s are there in this 100? Or if I'm constructing the second decision tree, how many data that I can use for my second decision tree?
1.
Only one data?
There are many samples, right, from
There-
100 rows.
So another combination?
Another combination means
Another sample, maybe
if
under
I use
60.
60 observation out of 100 observation, if I use the 60 observation,
50
how many
of-
observations I have left with?
40.
40. So typically speaking, for the second decision tree formation, I have to use the remaining 40. I have to use the remaining 40, and I'm just going to construct one decision tree. But here in decision tree, we are actually using the concept with replacement. So in statistics, you might study what is with replacement. So if I'm using that strategy with replacement, then I can also construct the next decision tree with other 60 data, right? Because with replacement means I'm allowed to use some of the samples which I have used to construct the previous decision tree. So that is actually with replacement. So it is not that the constraint is not like I should not use the same observation in multiple trees. I'm allowed to do it. That is the concept of with replacement. I can use the some of the part of the data which I have used for decision tree 1 to construct the decision tree 2 also. So even though there is only 100 observations, I can also construct 2 decision tree with 60 observation each, because after constructing this first decision tree, I have used 60, the remaining observations are 40, but it is not that only that remaining observation I have to use the construct the decision tree 2. I can also use some of the observation that I have already used for decision tree 1. So in that context, again 60 observations I can use and I can form the decision tree. Like that, how many decision tree that I can form now with the replacement?
100 C60.
Sorry?
100 C60.
100 into 60.
No,
But
100 C60.
100 C60. Fine, but anyway, it is like say, yeah, provided that the 2 tree samples are completely that is the same decision tree. Once again, I can't form in the sense like that you told 100 C something like that we can form. But anyway, I can form many n number of decision tree, right? I can form any n number of decision tree, right? So even if say some decision tree 1 and decision tree 2 is actually using the same data, the same 60 data, decision tree 1 and decision tree 2 is using in some other order, something like that, but the same data only, but it is using in some other order, then obviously that number of combination will further go. right? So obviously any high number I can form it. So it is not like only two decision trees, one with 60 sample and only with 40. The another one is with 40 sample only I can construct. With the replacement technique, I can construct multiple decision trees. So I can construct one another decision tree as
It is 100C60, right?
sorry.
It is 100C60, right? Total
Yes.
number of trees.
Yes, of course, mathematically, but provided that even say multiple time you are using the same decision tree, then in that case even the count will go up, right? So that say the same you are constructing two trees which is actually using the same data. Whatever the 60 data the decision tree 1 is using, the decision tree 50 is also using the same data in the sense even more than that C60 will go up. So anyway, we are actually ultimately not going to find that many decision tree and all. So we are going to restrict that with some small numbers only, because using many trees will actually overfit our model. So obviously the idea is with one sample data, with one data set, you can construct n number of trees. You can construct n number of trees. So here I'm just writing this as dtn. dtn. So multiple trees you can construct in this way, right? Now how we are taking this 60 sample? Randomly.
Where random sampling it is.
Right? So that is the reason why it is known as random forest. How we are taking this 60 samples? We are taking this randomly. So that is the reason why we are calling this as an random forest. Of course, why 60? Why not 40? Why not 50? Of course, this is an hyperparameter. You can actually construct decision tree with a different number of samples and see the performance. But in literature, if you see, the chance for one sample to be in the bag, say people will use to call this is bag 1, this is bag 2, this is bag 3, bag 4. Bag means people will call this is bootstrap, and also people will call this is bagging or bag. Out of this 100 sample, I'm just creating one bag with only 60 sample. I'm creating one another bag with other 60. I'm creating one another bag with other 60 combination. So this is each and every tree has been constructed with some bag of data, one bag of data. Now the thing is, there is statistically people will tell like the chance for one sample to get select in one bag, provided that there are totally n samples, the chance for that one observation to get select is 1 divided by n. So the chance that one sample is not to get select is 1 minus 1 divided by n, the whole power n. So this is a kind of formula that they have derived. So 1 minus 1 divided by n to the whole power n is the chance that one particular observation may not get selected in a bag. Out of 100 observation, you are creating some bags, then this could be a chance that this is an expression for the chance that one data may not get selected in one particular bag, right? So if you want the proof, you just search by yourself to how they are getting this. But anyway, this is a kind of the chance for one sample to get select is 1 by n. So the chance for that one sample not to get select is 1 minus 1 divided by n. But that whole power n they are using because there are so many combinations. So this is int like that. They have to expand this equation. So that is the reason why they have written as 1 minus 1 divided by n. The whole power n is the expression which gives that what is the chance that one particular sample will not get select in a bag or will not get select in one decision tree combination. So if you calculate this for high value of n, they are proving that for n as an high value, this whole expression is becoming some kind of constant. That constant value is around 0.36. The constant value is around 0.36 for high value of n. For high value of n, this expression is just become a constant, and that constant number and that constant value is actually around 0.36. So which means while you are forming the bag with respect to the n sample, that 36% of the data may not exist in that one bag. That is the idea. That is the kind of thing. So in bootstrapping or in this bagging concept, so out of 100 sample, so 66 percentage of the data is there in one bag. So like that, with replacement, you can construct multiple 66% size sample. So this is a kind of general analogy with respect to sampling strategy in statistics. But anyway, here in sklearn, here in machine learning, this is an hyperparameter. We are not actually using this formula exactly to define this. To define this, we are not going to be use always 66, because 36 means around 64, right? So we are not going to form our bag with a count of 64. This is an hyperparameter. We can play with it. We can play with it. So with 80%, what is the performance? With 70%, what is the performance? With 60%, what is the performance? With respect to that data set that we are having, we are going to be exploring in that way, right? So now you might understood like what is the concept of tree to forest and what is the concept of randomness. So randomly we are taking some section of the sample, randomly we are picking the samples using with replacement concept, so that we can construct multiple trees. So with respect to with all those multiple trees, so now say after doing this process, I have dt1, say I have dt2, I have dt3, I have dt4, and say I have dt5. Right? So before going into the discussion, can you tell me what could be the difference in terms of structure in these DTs? Do you think that all the root node for all the DTs will be the same?
No.
No, right? It is actually based upon what?
Based upon that root node, which we are taking a sample.
Information gain or Gini index.
Gini index. So for that section of the data, we are taking randomly 60 data, right? So the way that random 60 data may lead to the different Gini, right? So that is a different feature could have different Gini for that different section of the data. So we can't expect that same feature only is having the high Gini. Of course, in that data set that we are having like university admission, in that case, maybe all the decision trees may have initial root node as the same, because one feature is very dominant there. Do you remember that CGPA score? I think the CGPA score, that feature importance is too much there. So that is a very dominant feature. So in that case, many of the decision tree may have the same feature, but still for a proper random, for a proper complex, a little bit of data, obviously each and every root node now is actually get decided by the subsample. That is that 60 sample for this example that I told. So with respect to that 60 data only, we are going to compute the Gini. So with respect to that, we are going to decide which one is the root node and which one is the next level node and which one is the next level node and so on. So now say we have this 5 decision tree. Now I have one test sample. Now I have one test data. So now this test data, I'm just passing into, now there is only one test data. Now, but in my model, I have 10 decision tree. And please understand, these 10 decision trees are independent of each other. Are you agreeing my point? I'm saying the statement like this 10 decision trees are independent of each other. Are you agreeing that?
Yes, sir.
Right, because say for randomly I'm just taking 60 sample and I'm just going to construct these trees individually. So it is not like I'm seeing the output of one decision tree, based upon that I'm modifying or selectively taking some other portion of the data to construct the second decision tree, something like that. All those decision trees in random forest are actually independent of each other. So now say there is one test sample is coming. This test sample I'm applying into this decision tree. Say this test sample is actually flowing in this direction with respect to this decision tree, and it is giving me the output as is a defaulter. Is a defaulter. Defaulter, I'm just using D, and for non-defaulter, I'm just using ND. And I'm just applying that same test data, and I need to apply to all my decision trees now. So this decision tree is say traveling in this direction, and this is also saying that he is an defaulter. Now the same test data is going in this decision tree, and he is telling that he is a non-defaulter. It's not a defaulter. And with respect to this decision tree, it says it's flowing in this path, and say it is saying that he is a defaulter. And with respect to the last decision tree, fifth decision tree, it's flowing in this path, and say it is saying that he is a defaulter. He is a defaulter. Now, everyone first of all agreeing that each and every decision tree can take its own decision. Some decision tree may tell this test observation belongs to defaulter, and some observation for some decision tree it may tell that this test sample may become or maybe belongs to non-defaulter, right? So now out of this 5 decision tree, how many decision trees are telling that it belongs to defaulter, and how many decision trees are telling that it is actually belongs to non-defaulter? How many decision trees are telling that it belongs to defaulter, and how many decision trees are telling that it belongs to non-defaulters?
4 is telling that it belongs to defaulter, and third one it says that it belongs to non-defaulter.
Right. So out of this, 4 is actually telling that it is defaulter, and only 1 it is telling that non-defaulter. So your final model which consists of all the trees, will actually take the decision with respect to the majority opinion. Right. So here that majority opinion is what? Majority voting, max voting, or majority opinion. Here that majority voting is actually for the majority of the decision tree is actually going with the default case. So my final model decision is default. My final model decision is defaulter. So even if 2 decision trees are telling like it is a non-defaulter, even if the decision is like this, 3 are default and 2 are non-defaulter, still it is going to make a decision as defaulter, because out of those 5 trees, 3 trees opinion is like this particular sample belongs to defaulter. So I will go by the maximum opinion, max vote, right? So this is how this algorithm works. But whatever that I have explained, it's not actually random forest. Even though I have started this with random forest, and I have explained what is forest, and I have explained what is random. Randomness is like how we are actually constructing the multiple trees. How we are constructing the multiple trees. With respect to that, we have explained all those concepts, and we ended up with the count value like this. And with respect to that, I'm saying that my algorithm is taking the decision like this is defaulter. Of course, Maheshwari, if it is tie happen, as I told, whenever tie happen, generally your sklearn work go and see the class count. If tie happen in your data set, only 20 data are belongs to defaulter, and 80 data are belongs to non-defaulter. Your algorithm result will be get printed as non-defaulter, because most of the observation in my data is belongs to non-defaulter. So even though if tie happen here, if default count is also 2 and the non-default count is also 2, then obviously it will go with non-defaulter, because non-defaulter class distribution is more in my data. That is one thing, but we can avoid the tie very easily. How can I avoid the tie very easily? How can I avoid?
By taking odd number of trees.
Exactly, by taking the odd number of trees. So it is a kind of idea is, whenever the number of class that you need to predict is even, take the odd number of estimator, odd number of trees. Whereas whenever you are in the position to predict some class for multi-class, even you may be in the position to predict some class, 3 class, 5 class, like that. No, so in that scenario, take the even number of trees so that you can avoid the tie problem. So that is one idea. But apart from that, still, if you are taking the even number of n estimator for that odd number of levels, or for even number of levels, if you are taking the even number of n estimator, that is number of trees, then obviously the tie can be happen. If tie happens, a machine learning model won't throw any error. It will go and see what is the distribution count of your class label. So with respect to that, it will make the decision with respect to the majority count. Now, as I told, even though I have explained all those things with random forest, up to this, whatever that we have discussed, it is actually not known as random forest. It is actually known as bagging. It is actually known as bagging approach, bagging algorithm. But I have explained all the concepts as of now by saying that random forest, in random forest, what is random, and all those things. But at the end, now I'm telling that like this algorithm that I have just explained to you is bagging, which means random forest is also similarly works like bagging. The only one more extra randomness is exist in this random forest, right? So apart from that, whatever that I have explained now is actually known as bagging algorithm. So which means how bagging algorithm works? Bagging algorithm will works in the same way, like it will construct the multiple. So here I can take, I'm just writing the here as it's multiple what I mean by base estimator. Bagging algorithm construct multiple base estimator. What I mean by base estimator?
Decision tree.
Decision tree, right? But that is one another difference between your random forest and bagging. In random forest, the base estimator is always only decision tree. But in bagging, it could be any ML. Of course, you can't use random forest once again as a base estimator, but you can use logistic regression. You can use KNN. You can use Bayes as a base estimate. Of course, KNN will slow down. So generally, logistic regression and Bayes also you can use as a base estimator. Of course, decision tree you can use. Of course, decision tree you can use. Apart from that, you can also use logistic regression. You can also use an A-base as an base model for bagging, which means each and it will split the data. It will find the bag of data using the bootstrapping. Bootstrapping is the concept that I have discussed with you. So with replacement, if you are taking the sample from the data, overall data set, that process is known as bootstrapping. That bootstrapping will give you the different bag of data. Once you have the different bag of data, for each and every bag of data, you can construct the different models. So here that models can be, it is not that only you have to form the DT, you can also form the base model with Bayes, you can also form the base model with logistic regression. But keep one thing in your mind, both random forest and bagging are homogeneous model. What does mean by homogeneous? What is mean by homogeneous?
Similar.
Similar.
Which means you can use your base estimator, base model as decision tree or logistic regression or Bayes, but all the base estimators should be same. If you are constructing five base estimator or 5 models before making the decision, all the 5 models should be logistic model, all the 5 models should be Bayes, all the 5 models should be decision tree. You can't take like the first estimator, the first one is an decision tree, the second one is the logistic regression, the third one is the decision tree, the fourth one is the Bayes. Like that, you should not allow to take in bagging or in decision tree, bagging or in random forest. In random forest, all the base estimator must be the same, and also it should be only decision tree, right? There is no way that you can use the other models as a base estimator in random forest. But in bagging, you can use any of your algorithm as a base model, like logistic regression, base or decision tree. But all the estimators must be the same algorithm. All the estimator could be logistic regression, or all the estimators should be naive Bayes, or all the estimators should be decision tree. But you can't use for one estimator logistic regression, other estimation decision tree, other estimator Bayes, something like that. If you use different estimator for different ML models for different estimator, then that algorithm will become stacking algorithm. We will be discussing the stacking algorithm in our coming session. So as of today, whatever that two algorithms that we are discussing, bagging and random forest, are actually homogeneous in nature. Even boosting, right? So boosting is one another technique. Boosting is also homogeneous only. If time permits, today we will be discussing boosting. If not, in next session we will be discussing boosting and stacking, right? So in bagging, in random forest, in boosting, all the base estimator that we are constructing should be of same ML algorithm. Whereas in stacking, the base estimator that we are constructing can be from different ML algorithms too. So keep this point in your mind. All right. So this is one difference between bagging and random forest. Random forest will use only trees as a base estimator, but bagging will use other algorithms also as a base estimator. And also one another thing is, in bagging, the randomness in bagging, the randomness is due to row sampling. What I mean by row sampling? What I mean by row sampling?
Taking random samples.
Random sampling. Yeah, randomly we are taking the observations. So that is actually row sampling. Out of 100 observations, 60 observations randomly I'm taking, in the sense that is actually row sampling, right? But in this place only, your random forest is actually differs from your bagging. In random forest, randomness is due to both row and column sampling. In random forest, the randomness is due to both row and column sampling, which means, let me write it here. I told, like, we have 100x12 data. Using this 100x12 data in bagging approach, we have just created 60x what? Previously. How many columns?
60 or 12.
12 columns. But here,
Per parameter. Right?
I'm just introducing the randomness in column also, which means rather than using all the columns to construct the decision tree, randomly I'm just using the some columns. Say I'm just using only 4 columns. Randomly I'm just using the 4 columns. So this 4 is nothing but the random pick from this 12. Are you getting my point? This 4 columns is like randomly I'm just picking only 4 columns from the 12. Similarly, this 60 is nothing but the random pick from this 100. So randomness is exist in both rows and columns in random forest. So randomly I'm just selecting some rows, and randomly I'm selecting some columns. With respect to this, I'm just forming the decision tree. Right? Then in the it's a decision tree 1. Say again some other random 60 sample, some other random 4 columns. I'm just constructing the decision tree 2. Similarly, other 60 random rows and 4 random columns lead to the formation of DT3. Like that, I can construct n decision trees. I can construct any n decision trees. Got the point? What is the difference between bagging and random forest? If you remove the concept of column sampling from random forest, it's become simply an bagging algorithm. And also the another thing is random forest will use only tree as a base estimator, decision tree as a base estimator. In bagging, we are allowed to use other machine learning algorithms also as a base estimator. Apart from this, both bagging and the random forest will almost work in a same way. Understood? Yes or no?
Yes,
Sir,
sir.
sir, what is the if random forest and bagging are different, then what is the out of bag error in random forest?
See, in out of bag error is there in both random forest as well as in bagging. The only thing is, say the thing is, how they are calculating this out of bag error OOB. Say I'm just forming one bag 1, which is nothing but bootstrap 1. I can also call it as bootstrap 1. So bootstrap 1, say it's going to have the 60 data, and with this 60 data, I'm just constructing some base model. This base model is actually only decision tree in case of random forest, or it could be any kind of model with respect to the bagging. That is the only difference. Now, if I'm using 60 data, what is the remaining data? I'm constructing this decision tree or one base model with respect to the 60 data. What is the remaining data? 40 data is there, no? Say I'm just applying this 40 data into this model and I'm just checking the model predictability. That is actually out of bag error. What is the error produced by my model for that data that I have not used to construct the tree? So whether my model is predicting that 40 data correctly or not, to what extent it is making the error with respect to that remaining 40 data that I have not used for constructing this base estimator, constructing this estimator. That is actually out of bag error. Got the point?
Yeah. So, sir, the definition of bootstrap is something like we'll have a same number of samples, but it will be random, right?
Yeah, that even in it is actually internally we take care of. Say if you go and see each back size, internally random for us, how it, even in SQL and how it will do is, even though we will be giving from externally, we will be telling like take only 60 sample. Like there is an hyperparameter through which I can give 0.6. If I give 0.6, then say there are totally 100 data, it will take only 60 data. It will take 60 data. But if I go and see what is that back size, the back size will be 100. The back size will be 100. But in total itself, I have only 100 data. Then how can that back size is 100 irrespective of I'm instructing my model to take only 60 sample? What it will do is, it will do, even though it randomly picks 60 sample, some sample randomly exist in multiple times so that the overall data size will become 100.
Yeah.
Right, but anyway, logically that is a kind of duplicate data, right? Again some data that if you see the unique data, in terms of unique data, out of that 100 observation, only 60 unique observations are in your bag. But as it make everything to be work uniformly with it is actually defining that whole data set size with 100. So in that context, it is actually using that same data again for about 40 times, so that overall bag size will remain 100. But if you see the unique data, that unique data is only 60. So we are instructing that only through our hyperparameter, like how many percentage of the data it need to take a bag, it need to form a bag. Of course, it's using some of the data again randomly to equal that bag size to the same as that of your data set size.
Got it.
All right, fine. So now this is this is for the 60 data. It is actually constructing this, and with the remaining 40 data, it will apply on it, and it will see whether this estimator is having the ability to predict for that also. So that actually model is the out of bag error. If out of bag error is less, that itself a good indicator that your model is doing well. So this is about your random forest and decision tree. Sorry, random forest and bagging. So basically, random forest is also have a bagging as a part of it. The only difference between your random forest and the bagging, your random forest is actually use only decision tree as a base estimator, but bagging can use other machine learning models also as a base estimator. And in bagging, the sampling will be happen only in terms of row, right column, only bootstrapping is nothing but the process of selecting the random samples. But in random forest, both row sampling and column sampling is happening. It actually choose both rows and columns in a random way, so that the randomness of the random sampling will be high. So why we need this randomness? Can anyone tell?
To create different decision tree.
Overfitting, to work on the overfitting.
To overcome the overfitting, exactly, right? So which means if I think in the same point of view, I may be biased towards that results, right? So I let that other possibility to also to happen. So even though say one Guinea impurity value is high, so then say one Guinea impurity value is very low for one particular feature, then obviously that feature only is going to take a decision, right? So predominantly always that feature only is going to play a role. So if I'm just introducing the randomness, okay, let keep that particular feature aside, even though its Guinea impurity is very less, I'm just let that to be aside, and I'm making the decision with respect to the other feature. So I'm just introducing more genericness in my data. I don't want one particular feature is actually create the always play a dominant role in making the decision. So while I'm choosing the random pick of the feature, sometimes that CGPA, which is the very vital feature with respect to that admission data, may not be there in one random subsample of my column. So obviously, without the CGPA, what my model is telling, right? So obviously, the next powerful features may use to take the decision. Even though the decision is a kind of weak decision, I respect that decision also, right? So rather than taking one popular opinion and always one go with that, I'm just taking the multiple opinions for that multiple section of the data with respect to the multiple section of the data with respect to the multiple characteristics of the data in terms of the columns. At last, I'm just make that genericness. I'm just modeling that genericness. So even though I have not used that one powerful feature in one iteration or in one tree, of course, that powerful feature is going to be there in the other trees, other 2 or 3 trees. So at last, I'm just going to combine all the trees' opinion. I'm not going to take the decision based upon 1 or 2 trees only. I have, even though some trees are actually poor, some trees are powerful, I'm just letting the opinion to be made through different trees, and at the end I'm just ensembling the opinion of all the trees or all the base estimator. So I'm just this word is important. I'm just ensembling the opinion of all the base estimator before taking the final decision. So obviously I'm just introducing more genericness in my model. At the end, I'm just ensembling all the trees' opinion and making one stable decision. So obviously, random sample will actually do well in terms of both bias error as well as the variance error. Bias error as well as the variance error. Each and every tree that I'm actually forming will be focused on reducing the bias error. Each and every tree that I'm forming is actually focusing on reducing the bias error, because it will grow with respect to that 60 subsection of the data, how to fit it. So with respect to that, each and every tree focusing on reducing the bias error. But like that, I'm just not taking the decision with respect to only one tree. I'm just constructing the multiple trees and I'm just ensembling its decision. Because of that multiple tree ensembling process, I just reducing my variance error also. So random forest is the kind of powerful algorithm in which both bias error and variance error you can try to reduce it. So that is the idea of all the ensembling models, right? So ensembling model is Rather than taking the decision with respect to only one base model, we are actually constructing the multiple base model and making the decision. So under this ensembling, bagging will come, because bagging is taking the decision by ensembling the multiple results of different base estimator. And random forest is also an ensembling technique, and all the boosting is also an ensembling technique, and all the stacking algorithms also the ensembling technique. So bagging, boosting, stacking, like that people will define. But anyway, in between random sample or random forest is also there. Generally, people put the random forest under bagging version itself. But anyway, bagging, random forest, boosting, and stacking all are ensembling techniques, which means all those 4 techniques are using the concept of ensembling, which means it is having many base estimator, and at the end it is actually consolidating the results of all the base estimator and making the final decision, right? So whenever your algorithm is doing the process of consolidating the result of different base estimator and making the final decision, that process is known as ensembling process. That process is known as ensembling process. Now the idea is, the other thing is this bagging, boosting, and random forest are homogeneous. Homogeneous base estimator. Homogeneous base estimator, which means all the base estimator must be same. In bagging, you can use logistic regression, but all the base estimator must be logistic regression or naive or even decision tree. But in random forest, it must be only decision tree, and all the base estimators are only decision tree. In boosting also, you can use multiple base estimator, but all the base estimator must be the same model. If it is a decision tree, then all should be decision tree. If it is any other model, all the things should be the same model. But in stacking, it's suppose heterogeneous. Hetero base estimator. This is an underlying difference between your bagging, random forest boosting versus stacking. So stacking basically use multiple base estimator. That multiple base estimator can be from different ML algorithm. You can use one estimator as logistic regression, one as K-NN, and one as decision tree, one as random forest. Like that, you can do stack. So this is the
So if you so the base estimates are different. So how can we decide so it is correct or not? Because in bagging we have same estimator, so we can tell because of same predicting we are taking mode or any regression. But in stacking it is different models. So how it is good model? Because the open is different, right? From maybe decision tree open is different, logistic is different.
See,
okay,
is different means its math is different, right? So
yeah, math is different.
It is actually taking the decision based upon, say, whatever the algorithm, whether it's logistic regression, decision tree, the math is different. But what is an objective of that math? The objective of math is correctly capturing the effect in the output for the given input. That is what the math objective. That objective we are doing in the different way. So each and every way it's having its own advantage and disadvantage also. So decision tree in a non-linear way can capture. K using the distance, it try to capture. In logistic regression, it's using the linear regression concept to capture. So in starting, it is like we are actually utilizing the advantages of all the models. Say I'm just building the base model and I'm seeing that decision tree, logistic regression, boosting, AdaBoost is giving a kind of better result. But there is some kind of fluctuation. But out of the other 2 models, these 3 models are giving a kind of a result. Say AdaBoost is giving good result in terms of bias error, whereas random forest is giving the good result in terms of variance error for that particular data set. And logistic regression kind of explainability I may get, so something like that. Still, it is giving some kind of reasonable result. Then what I'm doing is I'm just making use of these 3 models advantage to stack, and I'm just stacking these 3 models, and I'm coming up with the final model, which actually is utilizing the advantage of all these 3 models, right? So ultimately, each and every model, even in stacking, these models are going to give their opinion. So with respect to logistic regression model, this is the opinion. With respect to the decision tree, this is the opinion. With respect to the random forest, this is the opinion about the class. Now I'm just combining all the opinion of the different models and I'm coming up with the final result. So even though the math is different, the main objective is same. Each and every mathematical algorithm that you are using for different machine learning models, the main objective is to relate the input and output. It is doing in a different way. Who cares? It is doing in its best way, and we are taking that output. And I'm what my logic regression is telling, what my decision tree is telling, what my random forest is telling, what my AdaBoost is telling. Out of this 4 algorithm, if 3 algorithms is telling in the telling like that person is having cancer, I just go with that opinion, because irrespective of different math, it is actually telling that the 3 algorithms are telling that that person is having cancer. So I'm just going with that maximum opinion that the person is having cancer. Right?
So compared to homogeneous, heterogeneous is the like, is there any fitting or any advantage? Overfitting or underfitting?
So,
Is there any advantage like that?
Like as I told, say if one algorithm is doing well in terms of bias error, if one another algorithm is doing well with the help of variance error, then in that kind of scenario, generally we will go with stacking, by stacking these 2 or 3 algorithms, so that in terms of both bias and in terms of both variance error, I will be getting the kind of good performance. Right? So like that only. So we can't really comment about say this is the kind of advantage always you will get with respect to stacking. This is a kind of good result always you will get with respect to bagging or some other strategy. So in machine learning world, we can't tell something like that. We have to explore all the possibilities for the given data set, for which possibility or which kind of algorithm is giving us the better result, that we have to piece as our final model. That is always the flow. But still, say one model is actually giving a very good result in terms of bias error, one model is giving very good result in terms of the variance error. So like that, you are having say 3 models giving good result in terms of bias, 2 models it's giving good result in terms of variance error. Then which model I have to pick? If I have confusion, I have stack all those model. Then I will take that stack model output as my final model output, so that I will be getting the better performance in terms of both bias as well as variance error. So that is the kind of idea. Right?
Thank you.
Fine, we will be anyway, we will be discussing that stacking separately, how to do it, all those things. So this is different ensembling techniques. Now let me move to
Sir, break, sir.
fine. Anyway, we can take a break. Then after you come back from break, we can take one data set, and with respect to that data set, we will be implementing this random forest. So
Thank
rather than doing the same thing with admission data set, I'm just sharing this data set. So while you come back from break, please everyone download this data set too. We are going to work on this data set just after the break. Fine. I hope everyone is back. Shall we start?
Yes, sir.
Yeah. So please download that customer data from that link, or you can also use that link directly in your Read CSV. So I have this data in my local machine with other name. So I just using that name. This data is having some information like churn risk, gender, status, children, estimated income, whether they are house owner or not, age, total dollar value traded, total single transaction. So like this is a kind of credit history, right? So a credit transaction of different customers, right? So the target column in this is we have to find that churn risk, right? So they are trading through your company. So you are a trading company, and there are different customers are trading through yours. So what is the churn risk? So how many people will trade continuously in your company, or how many people may actually leave your company? So that is what we are trying to predict here. The churn risk is having 3 levels: medium, low, and high. So quickly, our focus on building machine random forest algorithm on top of it, and seeing different aspect of it, like parameter tuning and what are the parameters that we can tune with respect to random forest and all those things. So just for a change, rather than using that same university data, I'm just using this data. So here the target column is churn risk, and it is having 3 levels. So of course ID I really don't want, but anyway, always ID information, customer name information, these are all the information we may need at the end after building our model, or doing some interpretation we may need, right? So for that purpose, if you want, you can also keep this as a set index. So I'm just keeping my ID as an index, so that now ID is not actually in my data. It's going into index. Let me show whenever we have a data in our hand, we need to understand something with respect to the output column. Before going into the input column, the very first thing that I need to understand about my data is how my output column is, how many levels are there, what is the level distribution, whether it is balanced data, imbalanced data. In this workout, I'm just going to address the imbalanceness also, or doing some kind of imbalance treatment, whether it is improving my model performance or not, using different imbalance strategy, how to do it. So all those things we are going to do in this session. So for that, understanding the target column is always vital and important before jumping into any kind of conclusion about what kind of model that I can use, all other things. So in classification, obviously our output data is always a categorical data. So churn risk dot value counts. I'm just seeing like out of this data, 983 observations are corresponding to the high class, and 699 observations are representing the low class, and 384 observations are representing the medium class. So if I want to see in terms of percentage, simply you can put normalize equal to true, so that you are seeing like 47% of data is representing the high class, 33% of data is representing the low churn risk, and 18% of data is representing the medium churn risk. So this is how that distribution is there in my output column. So of course, apart from that, I have few columns like gender, status, this, and also house owner. These are all some kind of other input column. The status is talking about its credit status, something like that. So it is not like the churn status. It is like about its credit credential status. So it is actually IBM data. You can go through the detailed code book for those data. So anyway, so now apart from this output column, I have 3 other columns which is actually having categorical information. So quickly just see what is the nature of those columns, whether you have multiple levels in it. If it is multiple levels, then going with one not encoding is a little bit hectic, because more levels is there, in the sense the number of columns will increase. So as of now, by seeing it, gender, status, house, homeowner, all those things definitely won't have that many multiple columns. It may have only a few columns, but anyway, if you want in some other data, you have more categorical column, and if you want to know how many levels exist, how the distribution, you can't keep on do with value counts for each and every column, right? So you can loop it. You can loop it in our EDA session itself. We have seen that. So if you want quickly, I will do it. Cat data, which is equal to data dot select the types of only cat data that I'm having. Now for I in cat data dot columns cat data of I dot value counts, right? So this you can print it, or you can also plot it. So here you can see only 3 levels. Here you can see only 2 levels. Of course, here you can see 3 levels. One level is actually 2 less. MSD, that is actually talks about the status of the credit transactions, and this is whether they are having the house or not, right? So fine. So it is not that much. None of the column is having too many levels, right? So it is a little bit difficult to encode it, right? So as only one or two levels is there, 2 or 3 levels is there in each and every of the categorical column. Generally, I can even go with one not encoding, because going with one not encoding, even though if it is an ordinal data, nothing wrong in it. But of course, going with an ordinal encoding for an nominal data will lead to some issues, especially that is also too much in linear regression. For non-linear model, to some extent, even you can actually go with, even though in terms of math we are not actually proving that, but still even if you have one column which is actually nominal, and even if you take some kind of ordered number to represent it, some of the nonlinear models like these are kind of insensitive to it. So it is not actually drastically changing the data, even though it is not healthy to do it. But of course, in some situation, you don't have any other option. Let us try that too. Even though it's a nominal data, you can just label and code it and see how your model performance is actually changing. So, but anyway, it is not encourageable. But still, I am saying that linear models are very much sensitive to it. Non-linear models are kind of less sensitive to it, even though if you use a kind of label encoding for an nominal data. But generally, only for an ordinal data, we will go for integer encoding or label encoding. For nominal data, we will be using some kind of encoding, one not encoding. Otherwise, we can go with target encoding, frequency encoding, and so on. Anyway, here all the number of levels are less, so one not encoding really don't make any kind of a big issue for me. But is it okay with go with one not encoding for the output column? In classification data, if you have a multi levels and if you want to try to encode it, is it okay to go with one not encoding for an output column?
No, it has to be binary. Only then one hot encoding works.
I think we can do, but without drop first.
Yes. No. The thing is, say whether it is nominal, ordinal, how it is actually creating impact on my model output, everything that based on that choosing that encoding technique is actually for the input columns. If it's an output column, obviously output I want to be as only one column, right? I don't want to keep 3 output column in my model, right? Of course, there is some kind of algorithm you can multi-target you can handle, but there is no point in it having the multiple output columns that actually derived from one single column. So generally we will be applying this logic of whether I have to use the label encoding or one not encoding only for the input side. Output side, if it is a level, keep that as level as it is, say medium, high, low. You can also keep it as medium, high, low, and most of the machine learning model internally can actually handle it. If not, if any error you are saying with respect to some scoring function like F1 and other thing, then obviously you have to keep like some levels. This is level 1, this is level 2, and this is level 3, because it is not actually in your machine learning algorithm is not actually going to do any kind of distance computation or any kind of mathematical computation by relatively seeing the output level. Say this is one level, this level has been represented with 1 and the other level has been represented with 2. Your machine learning model is not actually going to use the gap between that 1 and 2 to make some kind of decision, something like that. It is actually do that gap analysis, distance analysis, or whatever the other mathematical analysis with respect to the input data. So if this input data is like this is a level 1. If the input data is like this is a level 2. If the input data is like this is a level 3. Like that, only it will map your input and output. It is not going to use the difference between the levels in the output column to do any kind of mathematics of your machine learning algorithm. So in that sense, it is there is no issue if you go with some kind of typical integer leveling for your categorical output column, right? So it won't create any kind of impact on your machine learning performance. So here in this case, even the output column, I can actually keep it as 0, 1, 2, right? Even I don't need to worry about the order. Of course, here it is low, medium, high, so I can make it as 0, 1, 2. Even if you are shuffle the order, it doesn't make any sense because we are training the machine learning model. Say this is an input pattern, the level is 0. If this is an input pattern, then it is the level is 2. If this is an input pattern, the level is 3. So it's going to compare the input patterns for that level 1 and it's going to compare the input patterns for the level 0. It is not going to, while doing the comparison, it's doing some kind of mathematics, it's going to use only the input features. It's not going to use the output value. So in that sense, applying label encoding, it's not actually affecting your target column. But obviously, don't go with the one not encoding with respect to the target column. So what I'm doing here is I'm just keeping inp data dot drop off. I'm just dropping the churn risk. And here itself in out, and I'm keeping only churn risk. Then for that input, I'm just using say input 1. I'm just using get dummies. I'm just using in. For the out, even you can use replace low as level. So I have converted all those things. Now everything is number. Out is also just 0, 1, something like that. So now the data is perfect. So you can do a lot of other EDA also. You just do that later on. So now we are going jump into the model building. So quickly, I'm just going to split this data from sklearn dot selection import train and test train comma x test comma y train comma y test train test split of my input one, which is the dummy version, the out, which is nothing but my numbered version, and test size equal to say 0.3 comma random state equal to say 48 comma stratify equal to what is stratify? What is stratify?
Is balancing between the when we are doing sampling, we are taking balance when we are doing sampling, like equal ratio between the each class level.
See, out of this 100, out of 100 sample, 47% representing the high, 33% representing the low, and 18% representing the medium, right? So same percentage of representation I want in both my train and test, right? So sometimes what happens if I split, all the medium may go into train. My test may not have any medium, or my train will have a lot of medium sample in it. My test sample may have only very less medium sample in it. So I don't want such a kind of scenario. I want that equal distribution to be in the train and test. So that for that only I'm just doing this stratify equal to out. So even if you want, you can check this. Say in Y train, you could normalize, you can easily see 47, 33, 18, that percentage. If you see in Y test, it is also 47, 33, almost. All right, 18%. Only in the third digit there is a difference. So this is what that I want, because I want to give the same kind of experience to my machine, right? So with during the training and testing. So there is no point in training a model without one level, or there is no point in putting one level more in training, and there's no level for that corresponding class to test. So in order to avoid all those things, whatever the balance which is there in my overall data set, that balance that I am maintaining in my train and test portion also by using the stratify equal to true or stratify equal to out. So whatever the output variable that I have to pass, so that with respect to that out distribution, it is actually distribute your data in X train and Y train and Y test also. So that is an idea. So after doing this, quickly I'm just building the model from sklearn dot ensemble. Import, we have discussed, random forest bagging, boosting, stacking, everything is an ensemble model. So obviously all those function we are going to load it from this sklearn library ensemble. So sklearn.ensemble random forest classifier. So I'm just using rf underscore mod, which is equal to random forest classifier of as an empty object rf underscore mod dot it of data x train comma y train and rf underscore mod dot predict of your x test. So I'm just keeping in y thread. And quickly from sklearn dot text import classification report, and I'm just printing the classification. So this is the first level of result with respect to random forest. It's reasonably doing well, right? So overall, if you see the accuracy, it is 0.93. So you can trust the accuracy to some extent because this data is not too imbalanced. Whenever your data is completely imbalanced, then you can't trust your accuracy score. And also you can see your F1 score, macro average is reasonably doing well, 0.90, 0.89 in terms of recall. In terms of precision, the average of all those three classes are 0.92, right? So, and also for with respect to the zero class, the model is doing well in terms of precision, recall, and F1 score. And also in terms of class 2, the model is doing well. Class 1 is actually zero, low risk, and 2 is high risk. In terms of low risk and high risk, your model is doing well. Of course, in terms of medium risk, there are some misclassification. That could be true, right? So it is a little bit it is a little bit tough to detect the medium risk, right? So medium risk can be going anyway. So they may churn out or they may be in the company. So of course, my model recall is actually kind of kind of less with respect to medium risk, and also F1 score on the kind of lower side compared to class 0 and class 2, but which is quite expected in this kind of domain where I have to classify something as low, high, and medium. Low and high, maybe the values are kind of discriminated, so my model is identifying that pattern well. Medium could have gone in either way, so that is the reason why there is some kind of lag in the performance, but it is not actually too poor, something like that, even with respect to the one class. It is fine. So, but anyway, the one another reason why that one class data is or one class performance is kind of lag compared to 0 and 2. Can anyone tell what could be the reason? What could be the reason? What could be the reason?
A lower number of sample.
Lower number of sample, right? Yeah, Raghu, I'm just coming to it. I'm coming to all those hyperparameters with respect to the random forest. What is the kind of sample size it is using, what kind of technique it is using, how many trees it is using, all those things we are going to discuss now. But before that, I will address this. So now if you see that that one group count is actually kind of less compared to the other group. For that one group, one class, which is nothing but medium class, only 18% of representation. Whereas for 0 class and 2 class, 33% of representation and 47%. So 18 is actually kind of off of this 33. So it is not too much representation is there for that medium class. So that is the kind of, that is one reason why my model is not able to learn properly, because the representation for that medium class is actually less in this data set. One thing is you can increase the data. One thing is you can increase the data. You can speak with your client and you can increase the number of observation with respect to the medium class. But most of the time, client won't be in the position to supply more data because he already shared all the data with you. So that is the data that he have. So obviously you have to do something to come up with the better trustable model with the data that you are having in your hand, right? So always in data science, more the data will actually give the good inferences. Your model predictability may improve, true, but we don't have that option of getting that more data always. So in that sense, what I have to do? So I'm just going to discuss on that part before going into the different hyperparameters of that random forest algorithm that we have implemented now. So now, how to improve or increase one class representation? How to increase one class representation? So here I won't say that this class representation is too poor. It is not actually highly imbalanced, but still there is an imbalancedness. But how to overcome this, or how can we explore some other strategy to bring our data kind of close to balance? Say for that the strategy is upsampling and downsampling. Upsampling and downsampling are the strategy through which we can actually balance our data. So what is meant by upsampling? Upsampling is also known as oversampling. This downsampling is also known as undersampling. So say I have some data in which 90 data is representing cancer and 10 data is representing the let me take like this. 90 data representing the cancer and 10 data is actually representing the cancer and 90 data representing the non-cancer. Now obviously the data is imbalanced. So now my machine learning model need to understand about the cancer characteristics by seeing only this 10 data. 10 data is not good enough for my model to learn the characteristics of it to make the generic decision. Whereas for to represent the non-cancerous data, there is 90 observations. So it will just learn lot in an effective way with respect to that 90 observation, but equivalently, we are not actually giving more representation with non-cancerous data. So my model ability to understand the cancerous pattern is little bit less. So what is the kind of idea? The idea is I can increase the sample count, increase the sample count, but how to do it? How to do it? Any kind of sampling techniques that you came across during your statistics course? Any upsampling technique? Any upsampling technique? One raw way is just repeat the representation of some sample. Just repeat some representation of some sample. So out of this 10 sample, I'm just taking the few samples and again I'm just duplicating that data. Again I'm just duplicating the data. That is kind of approach, but it won't really help my machine learning model because most of my machine learning model will tend to tune itself by with respect to some kind of uniqueness in the data. By again repeating the same data, it's not at all going to help my machine learning model algorithm to understand the unique pattern in the data, right? So because while it's tuning its weight, while computing its distance, if these things are remain same, then obviously it is not going to help my machine learning model to understand anything better with that newly introduced sample, which is just a copy of already available samples in that minority class. So what we can do is in Python we have one package called Smooth. There's an algorithm called Smooth. So what Smooth is doing is it is synthetic minority oversampling technique. So this is a synthetic minority oversampling technique. So with this, I can do oversampling, which means upsampling. So this Smooth technique you can apply only for the minority class. Whenever there's a minority class between these two, non-cancer and cancer, cancer is a minority class because the count representation for cancer class is less. So it will actually try to pull up the minority class such that it will become equal to your majority class. So after applying Smooth without any argument, simply I am applying plain Smooth, then it may become even 90-90. Non-cancer and cancer. But what is the problem with this? So if I made this count 90-90, say I'm just synthetically generated too much. Maybe the characteristics of the newly generated data maybe overfit my model or may actually not really represent the real scenario of the cancerous patient, right? So I can't simply do the minority oversampling technique such that with an objective of equaling that size with respect to that majority class, right? So I have to up, or I have to increase the count of the minority samples such that whether my model is actually getting some kind of learnability. So it is not always required that we need to do 90-90 only. Even sometimes from this 90-10, I can do like 90-20 or this 10 alone. I'm just pushing that 15 units, say 25. So initially it was only 10. Now I have pushed that count from 10 to 25. Now if my model performance is reasonably good, so with respect to this extra 15, my model now learning the pattern about the minority class, then it is well and good for me, right? So always don't have fix your mind like balancing is nothing but just making this two distribution exactly equal, right? So it will actually mislead. It actually change the overall characteristics, right? My model may wrongly understood about the cancerous pattern. If I keep on synthetically increase the cancerous pattern to very high values, so just increase it, just aid your machine learning model such that it can get some kind of understanding reasonably well. So leave with that, right? So don't try to overcompensate or don't try to too much oversampling will lead to some kind of mislearning by your model. So how to do it now? How I'm doing it? Whether I'm just increasing 10 count or 20 count or 30 count. Anyway, I need to do the upsample. I told that repeating that sample simply again and again won't help your machine learning model to learn anything reasonably out of it. So what kind of strategy that I can do so that I can smartly synthetically generate the new samples? The idea is say you have a class like this. Right? So now, which one is the minority sample? Which one is the minority class in this diagram? So this one is the minority class. Now, your algorithm randomly pick one sample in this minority class, right? So it used to identify, say I'm just drawing one another sample here. So now out of this minority class, it will just take one sample and it used to find some neighbors for that sample using that same distance algorithm that we have discussed with respect to KNN. Say if I ask you what is the three neighbors with respect to the sample, you may tell
within minority or
within minority only. Within minority, your SMOT won't do anything with respect to majority.
Okay.
Right. So now with respect to this minority, what is it? For one given single sample, which is three neighbors, it will calculate. Once it calculates that, so this is one neighbor, this is one neighbor, and this is one neighbor. So of course you can control this, whether you want to see the three neighbors or five neighbors or seven neighbors or any n neighbors, right? So here I'm just explaining with three neighbors. So these are the three neighbors, right? The other two samples are a little bit deviated away from this. So these are the two neighbors. Now what it will do is it actually identify the neighbors, and in that neighbors path, now it will actually introduce some samples randomly. So randomly it will just introduce some samples. So now the cluster is like this. So here initially 1, 2, 3, 4, 5 points only. Now in this path, randomly it is actually in this neighboring path, randomly it is introducing some samples. So now from 5 samples, now that orange line, if you see 1, 2, 3, 4, 5 samples, now it's become 10 samples. From 5 samples, now the count has been increased to 10 samples. Now if you see the overall characteristics has actually remain same, right? I'm not introducing the same sample on top of it again and again. I'm just say this data has been clustered like this. So now in this path, one data is here and one data is here. Some data may be here, right? So in that direction. So I'm just picking one sample and I'm seeing what is its neighbor. In that neighbor's path, randomly I'm just introducing some sample. So the direction of the data, the distribution of the data will be, the characteristics of the data maybe remain same as that of the original one, but at the same time I'm not exactly duplicating the data. I am just getting the new data which is having a kind of same characteristics of my old data, my other data. So that is the idea of a SMOT. SMOT is actually generating the new sample in this way. Are you getting the point, everyone?
Yes, sir.
So iteratively this process will happen. Iteratively this process will happen. Again, it will take some other samples, some other samples, and it will use it to identify the closest neighbors. And in that closest neighbor path, it is used to introduce some new samples, so that we will be introducing the new samples in a reliable way. We are not just merely duplicating it, but at the same time, we are not actually introducing something which is completely different from the characteristics of that class. So that is the tool idea that SMOT is doing, right? So this is one way.
Sir, until when it is done, this iteration process?
This iteration process, it's based upon to what level you need to upsample. Say that control is there in that function. Let me show that. But suppose say if you want to completely become this class to balance, then say here I told no 90-10. So if you are applying this mode such that I want both the class distribution to be same, then from this 10 until this count becomes 90, it will keep on do that. Got the point? Yes or no?
Yeah.
From then, it will keep on introduce some neighbors in that neighbors path. It used to do it compute some neighbors in that neighbors path. It introduce some new samples. This process will keep on continue for different samples in that minority class until this count is become 90. Once the count becomes 90, it will stop. But before that, at any point of time, you can start. You can stop. So you don't want that level to go to 90. You want to increase only from 10 to 30. 30 you have give as one parameter, so that once the count becomes 30, it stops. That is the idea.
So this new addition is within that same particular class, right? Within the red samples itself.
Only within the red sample.
What if the sample taken is itself in the border?
Sample?
For example, if the sample which is taken is itself on its border, so will it again, like, is the how reliable is the learnability? Like,
no, see, I'm not getting your question. So you are asking like how if one point has been considered as its own neighbor.
Correct.
But that is not possible, right? Say it is randomly picking one point and it is seeing that what is its nearest 3 neighbors. So obviously the nearest 3 neighbors are something different from that particular point, right?
Okay.
I think in case of outliers, it's possible. So you have to remove the outlier and then you have to apply a SMOT.
Asking like say the neighbor is actually from the other class.
No, the other class will not be even considered. That I understand. But in case if as Nitin was saying, like if it is an outlier, then also the same treatment. I mean, like, should we need to treat the outlier and then?
Yeah, obviously the SMOT will actually kind of say that the thing is, say you have an outlier, then in this distribution you have one point somewhere here. You have one point somewhere here, or you may have one outlier point which is actually close to even this green distribution somewhere. So obviously in this case, if you consider this as a neighbor, or if you consider this as your seed point, to consider a seed point with respect to the seed point, it actually used to consider its three neighbors. Say if it is a seed point, the three neighbors are something like this. So this one, and this one. So obviously it will introduce some samples in this path, which actually may change the characteristics of the data. Of course, your SMOT is actually kind of sensitive to the outlier. But anyway, the chance that random sample randomly while it is picking, the chance for that your algorithm to pick the outlier is actually less, right? Because if you have a 10,000 samples, or say if you have 1,000 samples, in the 1,000 samples, the number of outliers could be less. So while it's randomly picking each and every sample, the chance that it is picking the outliers are less. So with respect to that, even if it is picked that by chance, and that few new points it will introduce in that outlier path. So obviously that is also going to be a kind of outlier still. But anyway, it is not like it's completely changed the characteristics, because as majority of the sample is in this place, majority of the neighbor it will choose from here, and because of few outliers, maybe it may choose that outlier as a seed and it will introduce few points, but it won't very much in that impact will be not that much. And also if you don't want that effect also, then if you do the outlier treatment on top of it, if you do this sampling, then obviously that problem also you can overcome, right?
Yes, sir. Yes.
And also one another strategy that people use is rather than only doing the upsampling, you can also do this on downsampling. Of course, downsampling will lead to some kind of information loss. But say there is some credit card malfunction kind of analysis that you are doing. Your percentage of one class is 99 and another class is just 1. So in that case, rather than only concentrating on this, I will concentrate this too. So I will reduce this. So I will try to increase this by say unit of 20, and I will reduce this from 79 say some 80. Now it is kind of reasonably good compared to this. So which means here I'm just doing the upsampling. Parallelly here I'm doing the downsampling. Right? So that kind of strategy also you can do, but of course we are losing out some data here, but still using algorithm like near miss, like SMOT, there is one algorithm called near miss. So the near miss algorithm will actually drop the data which is actually very close to the other class, So one data from this distribution is actually very close to this distribution. Then obviously it will drop that kind of data. So obviously that will actually help your model to learn a little bit well, right? Because whenever some data is actually close to both the classes, then obviously your model will confuse whether from this data making a decision about whether it belongs to class 1 or class 2, my model will always have some kind of confusion. So near miss will identify that kind of boundary data, and it will remove those boundary data, so which will actually help your model to learn well. At the same time, you are reducing the majority data count also. So that is the kind of there are different algorithms for downsampling also. Near miss is one good algorithm. So you can also use both near miss as well as SMOT parallelly. So on one hand, you are trying to increase the minority sample, on the other hand, you are trying to reduce the majority sample, so that you can achieve that balanceness or required balanceness. When I'm saying balanceness, I'm not talking about 50-50. The balances that you required for your model learn can be achievable very easily. So like that, you can apply different strategy. Quickly, let me show how to apply SMOT. From sklearn model selection in order to from IMBlearn. I hope it is part of your Anaconda itself. If not, you please install it. IMBlearn oversampling import smooth. So I'm just creating one model as smooth of, I'm just giving k neighbors. By default it is 5. That is, I don't know how many neighbors it need to pick. So by default it is 5. But of course you can all again explore your model for different neighbors, how it is actually affecting your model performance. Then here I'm just giving one another argument as sampling strategy. Through sampling strategy, what I'm going to do is, can anyone tell what is your count of your medium? Normalize equal to true. I'm just removing it. The count is 384. So now what I'm going to do is, as I told, I'm not going to do this in a way that all the class count should be equal, something like that. So what I do is, I'm just increasing this class count to some value. Say I'm giving like sampling strategy, I have to give it in dictionary. So all the values also you can give. But anyway, here my task is only control this 1:500. So from 384 or 384 or what? From 384, I'm just increasing this one count only to 500. So 1,500. Of course, random state initially I'm just giving, simply because if I run for the second time, the same neighbors it has been chosen need to be chosen for the second time also. So for that case, I have given the random state equal to 100. So this is the structure. Once I have the structure, and I'm just using the fit resample. Yeah, the method in IMB learn is fit underscore resample of my input version 1, that's a dummy data, comma out. So this I'm just sorry.
I mean, once it is done, please ping that in the chat, sir.
You want me to copy this in the chat?
Yeah. Second.
Yeah. Sure. I will do it.
Okay, sir.
So I have resampled it. If I see what is my out balance, now you can see from 384, I have increased that count to 500. Now the balance is to some extent I have achieved, but of course my objective is not like equal distribution, something like that, which will actually mislead my model at many a time, generally. So I'm just 100 unit or 120 unit of one sample count I'm just increased. So with respect to this, now I'm just going to build my model. With respect to this balanced version, I'm just going to build my model. So once again, I'm just splitting this. Input val and output val, and also here stratify, I have to give output val. I just copy paste this in chat window. So I have implemented the, I have once again splitted the data. Of course, keep it this as extra in one. Anyway, let it be. If you want, once again, we can run that. Xtrain, ytrain, expressed ytest. Then I'm just building my random forest model. The same code, I'm just copy pasting it. So Xtrain, everything is same. So let it be. I'm printing the classification report. Is any improvement with respect to the class 1? Without much of sacrifice in other classes? Yes or no? Yes or no? Here, just note down. These are the numbers. For class 1, it is 0.86, 0.74, 0.89. 0.86, 0.74, and 0.89 are the numbers for your class 1. So in terms of precision, there is 1 unit of decrease actually after doing this imbalances. But recall from 0.74 it has been increased to 0.78, and also F1 score from 0.79 it has been increased to 0.82. Overall model performance also in terms of recall and F1 score, there is a slight improvement, right? Especially with respect to the class 1 for recall and F1 scores, there is a reasonable improvement. Around 4% improvement in terms of recall and 4% improvement in terms of F1 score has been achieved by slightly upsampling the count of my class 1. So I'm just giving a little bit more learnability about the class 1 by using that SMORE technique that we have discussed, how it is actually introducing that new samples in our data, which actually aiding my model to learn about that medium class, right? But we can't expect for medium class that result to be very high, because medium class is a kind of medium risk person. So medium risk is actually whether they will stay with me or not stay with me. I can't take that decision very effectively with respect to the medium risk person. So it is always we can expect some kind of a low performance there. But anyway, you have to make sure that say if you are feeling like someone is medium risk, at any cost you don't want to lose them, right? So even though your model is wrongly predicting that people as medium risk, you are going to do some kind of you are going to make a call to him, or you are going to give some kind of offer to them. So you have to make sure that you are making sure that they are staying with you, right? So in that context, you want kind of recall to be high for medium risk, which means none of the correct medium risk should not wrongly classified as low risk, something like that. You want that to be on the correct prediction. So you want the recall value to be a little bit high. So compared to the previous model here, 4% of recall we have achieved. So in that sense, it's fine, but too much of oversampling may change the characteristics. So if you increase that number, so what happens is other numbers will start to reduce, because your model now will learn more things synthetically, because as more the synthetic data that you are introducing in your model, you are changing the characteristics of the data, and you are making your model to learn your synthetic data. So there is no guarantee like your synthetic data is very much same as that of your original data, right? Of course, even though we are doing this SMORE k neighbors concept and all those things, we should not introduce too much of syntheticness in our data. There is no point in actually having a lot of synthetic data in our model. So in that context, just increase bit and see. Still there is a scope for improvement, even increase from 500 to 600. So like that you have to explore with respect to your minority class. Fine. Any doubt in this? Yes or no?
Yes, sir.
Yes, sir.
Fine. So now let us quickly go into the tuning of this is one thing that I have done with respect to this model output to improve its results. Of course, we have done slight improvement in terms of result, especially with respect to the class 1. But this is not only for random forest, right? So this is actually a kind of common technique that you can apply for any machine learning model. Now, quickly we can do a kind of analysis to understand how many trees that I want to construct for this random forest. So I told that random forest is having the collection of trees. So what kind of random forest will always using this bootstrapping strategy. So it is going to take some samples, but how many samples it can take for each and every bag, that is in our control. How many trees it need to construct, that is in our control. How many features that it need to take, because column sampling also is the technique, is an hyperparameter. Column sampling also is happening in random forest. So how many columns it need to take, how many samples it need to take. Of course, sample it need to take only with replacement only, that is in bootstrapping way. But how many samples it need to take, how many columns it need to take, what kind of how many trees it need to construct. These are the kind of hyperparameters. Apart from these three hyperparameters, whatever the hyperparameter which is there in the decision tree is there here in a random forest also. Are you agreeing that? That max depth, minimum sample spread, minimum sample leaf, right? So criteria, all those hyperparameters which is there in the decision tree, it is there here in random forest also. Apart from this, these three are the extra hyperparameters. One is how many trees. How many trees is one hyperparameter, and the other thing is how many samples. How many samples and how many columns. How many columns on which we are going to construct. So these are some kind of extra hyperparameters that we need to focus on, or that you can explore while you do your grid search CV, right? So apart from that, all the DT parameters, because decision tree is the hyperparameter base estimator in random forest. So obviously all the DT hyperparameters are actually the hyperparameters for your random forest also. So now let us first explore one hyperparameter, which is nothing but how many number of trees. So I'm just going to construct my model for different number of trees, and I'm going to compare the performance. So for I in the same way as we constructed before for decision tree, I'm just going to construct this. Say 5, 10, 15, 20, 25, 30, 40, 50, 70, 100, 120, 200, 300, 400, right? So this is the for the number of trees. So I'm just going to construct 5 trees with with replacement concept, and 10 trees with replacement concept, 15 trees with replacement sampling, 20 trees with replacement sampling, so on. So we have discussed. Even if people told like that NC times we can construct, right? So any n number of trees that we can construct. So I'm just going to export my model for this numbers of trees which I have specified within this list. So now I'm just constructing my random forest here. RF equal to random forest classifier of, here the hyperparameter through which we can control the number of trees are actually known as n estimators. So n estimator is the hyperparameter through which we can give or we can pass number of trees information into my random forest model. So here I'm just giving us height. Here I'm just giving us height. And as we know, there are so many other hyperparameters. So for each and every iteration while it is actually running for this I don't want the other estimators or other arguments of the random forest to change. So I'm just freezing the all other parameters with random state equal to 48. So whatever the value it is assuming for the other parameters, it will remain same, and only the n estimators will change. So now after this, I'm just using the score. Of course, this is a multi-class problem, so I need scorer. Scorer equal to make score. Make score or scorer. I have to load those libraries. So from sklearn dot model selection import cross-val score. Then from sklearn metrics import make scorer and also CF1 score. Now here
Sir, n estimators, what did you say?
n estimator through which we are going to explore our model for different number of trees. So in random forest we have multiple trees, right?
Yeah.
So say if I construct my random forest model with only 5 trees, what is my model random forest
Then
performance?
1 by 1, 10, 15, 20.
Yes.
So this is a little different from base estimator, right?
No, this is not at all base estimator. In
Yeah,
random forest,
different from.
in random forest classifier, we no need to give the base estimator because the only one default base estimator for random forest is decision tree.
Okay. Yeah.
Right? So make scorer of F1 score, and I'm just giving the average, even weighted I can give. So here I'm just giving as weighted. Previously I have given macro, right? Macro means just on simple average, weighted means weighted average. So now I'm just calculating the score. Score equal to cross-val score of my model RF, comma my scaled my balanced data input balance and output balance, comma CV equal to say 5, comma scoring is equal to scorer. So I want to print all those things. So I'm just printing it. Print what is the N estimator. Even if you want to create a scorecard, you can create it. But here I'm just printing it. N estimator is there in I. And I want to print my bias error. Bias error, I have to take NP dot mean of my score. Then I'm just printing the variance error also. NP dot SPD of score, the whole divided by NP dot mean of score. So coefficient of variance. So I just want to previously for KNN we have draw the graph, no? So similarly, if I want to keep all those information, bias error and variance error, I can append it B dot append for each and every iteration. What is that? So bias error, I can say error. So here I can't tell as an error. If I want to tell this is an error, then I need to put this as 1 minus. So here I'm just appending this 1 minus mean dot score. Similarly in VE, I'm just appending it as this formula. It's running for each and every I value. In other words, it is running for each and every N estimator value, and it is actually giving the results. By going through this result, we can understand like for which N estimator the value is less in terms of bias error, the value is less in terms of variance error. But sometimes it is a little bit difficult to go through all those numbers to make the decision. So we can plot it. We can plot it. Plot of this list I'm just taking. Otherwise, Matplotlib will actually define its axis by its own. Comma B. I'm getting something like this. Similarly, you can plot even variance error. The variance error is coming like this. Of course, this is some scale and this is some scale, right? So of course you have to spend some time on actually seeing this as a graph or seeing this as a number to understand for which estimator. See this, the bias error is actually kind of very low after 100, but after 100 if you see the variance error, the variance error is actually shooting, right? Yes or no? See, your bias error is actually very low, especially between 200 to 300 and all. It is actually low. From 100 itself it start to reducing, right? The variance error is less, sorry, your bias error is less for a high end estimator. But for high end estimator, what happened to your variance? What happened to your variance error? It is very high, right? Not very high, but anyway, it is high, right? In the scale. Yes or no?
Yes, yes.
So which means high taking too much of opinion. An estimator is nothing but what? Constructing so many trees and seeing what is the opinion of each and every tree, ensembling that result to make the final decision. So while you are making some decision in your life, if you ask some trustable person, it is fine. If you ask so many people, then everyone will come up with their opinion, and at the end you will confuse and your decision may go wrong, right? So that is what here exactly happening, right? So that n estimator is high, that variance error is becoming high, kind of high. Even you can do something smartly. Try to bring both the graph in the same both these line in the same graph, so that you can compare it. You can do the comparative analysis very effectively. But the problem is, if you bring both the graph in the same both the bias error and variance error in the same graph, then you have to scale this numbers. You have to normalize this number, because here the value is 0.07 to 0.08. Here the numbers are not at all close to 0.07. So obviously it will come in somewhere, that graph will come somewhere. So quickly I will give one approach just to give an idea, so that for the other works we can do it. So I'm just creating something called B1. So B1 is equal to PD dot. So I'm just going to do some division. So if I have it in data frame, it is easy for me. So PD dot data frame of B divided by PD dot data frame of B dot sum of. So what I'm doing, I'm just normalizing it. I'm just summing up all the B value, and I'm just dividing each and every B value with the sum, in the sense now that scale kind of defined range. The same thing I'm just doing with variance error also. All right. So now I just scaled the values of B1 and V1. Now after doing this, I'm just plotting the same. I have to copy the same list. B1, of course, this is a data frame. So by default, it actually have a column title as 0. So I'm just putting as B1 of 0. And similarly here, I'm just putting as B1 of 0. Why that I'm putting B1 0 1 0? You can understand here. So here that column title by default is coming as 0, no? So that is the reason why I have just mentioned that as B1 of 0, because that column I have to plot it against this. So now if you see, now I'm just getting a kind of proper graph, right? As I scale down, so only the point that you need to see, at what at which place. So by seeing this, which value of n estimator that you can go with? Which value for n estimator you can choose? Let me copy paste this. Even if you want to increase the figure size, to stretch this out, SI is equal to say around 12 unit in x-axis. Only x-axis I want the stretch. Fine. So what is your take? By seeing this graph, which value that you can choose for n estimator? Which value you can choose for n estimator?
130.
Hmm?
130 or 70. You can take. 130.
130 here.
Yeah.
Why?
Between 50 to 100, I think. 70.
70 also we can.
Right here.
70.
So this which one is out of these two graphs? Which one is actually this number is B. This number is actually B. I think we have to put. Yeah. So blue is B, bias error, and that orange line is variance error. So Joseph is telling that 70 to 80. Okay. So here, this peak you are talking about.
No, sir,
Fine.
not the peak. I think that joining point next to that. Yeah.
Point. Yeah. So this joining point. Okay, that could be one idea. Like both bias error and variance error are
Less.
equal, right? Because it is crossing that, and also here it is crossing. But while it's crossing, that overall error is little bit high. So this is the least point where by crossing the value is less. I can also go with this n estimator of 25. Right, but of course there is a gap, but with the n estimator equal to 25, both the values are low. But of course there's a gap, but you have to see this gap is very too much or not, because here I have scaled. Don't just go by this amplitude of this graph, because this is the scaled one, right? So at n equal to 25, you just go and see what is the variance error and what is the actual bias error and what is the actual variance error. Just go and see when n equal to 25. When n equal to 25, see this one. Your bias error is 0.07 and variance error is 0.01. That is coefficient of variance. Coefficient of variance is about only 1%, right? So that is the least point. At that point, whatever the bias error is getting us around only 7%. If this is fine for you, then you can go ahead. You can go ahead. Otherwise, as Joseph is telling, this is also one good good point to explore. So here it is at this point, both the things are actually less. So between you can also include some other n estimator in your list between say 70 to 80. How far between 70 to 80, how the values are, you can see, so that with respect to this point, you are actually not having any overfitting, because your bias error and variance error are same, but at the same time this is on the kind of lower side. But anyway, still you have a point where the variance error is much less also, but of course the deviation is less. But of course whether the deviation is more, but of course this deviation with respect to the scaled number. So you have to go and see in your data or in, with your other printed values for n equal to 25, what is your bias error and what is your variance error. That is fine for you. You can go ahead with that. So like that, you have to carry on. So plotting it in a different way will actually help you to understand which n estimator or which hyperparameter is doing well. Now the same thing you can do with grid search CV also. The same thing you can do with grid search CV also. I just quickly do that just for the sake, because nothing newly we need to do. We're already doing this for other models also. So for models from sklearn.model selection, import grid search CV, and params I have to define. So here once again I'm just exploring what is the n estimator my grid search is giving. We already explored the n estimator. let us see what is the n estimator that grid search CV is giving. So n estimators, I'm just giving 10, 20, 25, 30, 35, 40, 45, 60, 65, 70, 75, 80, 85, 90. And the other estimator that I can give is say max feature. Can anyone tell what could be this max features? What could be this max feature hyperparameter?
Columns.
Maximum feature by splitting.
That is column sampling. I told no. So how many features that we are going to take? So here it will accept some string, right? So like auto means automatically randomly it will take some numbers, and the other thing is you can give square root. If you give square root, then what happens? Say if you have 12 columns in your data, what is the square root of 12? What is root of 12? 3 point something, right? So 3 point something, it will round off to 4. So randomly it will take four features. Randomly it will take 4 features if you give square root, right? With respect to 12 features, 12 features data set I'm telling. Here I think we are having 23 features. Root of 23 is around 4 point something, so 5. So it will actually take 5 features at a time to build the model. Then there is one another option also you can give here as log2. Log2 is, say if you have 8 features in your model, log2 of 8 is nothing but 3, right? Yes or no? 2 to the power of 3. So log base 2 of 8 is nothing but 3. So for 8 feature, it will take only 3 features. It will take only 3 features, and with respect to the 3 feature, again it will for a random pick of 3 feature, again it will build a decision tree. So like that, you can explore max features for which of this method your model is giving you the good thing. And also here, as I told, you can also use max depth. Yes or no? Each and every tree, to what extent, only up to what level you want to grow. I'm just giving 10, 15, 20, right? So just only that I'm just giving 10, 15 and 20 because it takes a lot of time. And also you have max samples, so you can go and explore your random forest classification, sklearn dot random forest classifier. So you can see all those parameters here: criteria, n estimator, min sample. So whatever the min sample left, whatever is there in the minimum impurity decrease. So all those things are there in our decision tree also. Those things are there here also. OOB score, whether you want that out of bag error score, these things also you can give. And here you can see max sample, right? So max sample you can give in terms of fraction number, anything between 0 to 1. So if you give 0.6, 60% of samples has been used for that bootstrapping. So if you are giving 0.8, 80% of samples will be used. So like that, you can play with that, play with all those parameters. Now I'm just giving one another thing, just if you okay. Otherwise, I just run with this. I don't want to give more parameters now. It will take a lot of time. So once I defined all those parameters for which you want to tune the model, so RF mod 1, which is equal to say random forest classifier of, and say hype mod, which is equal to research CV RF underscore mod 1 estimator, then param grid equal to params, comma scoring equal to scorer. Because it's a multi-class, so I have to give the scoring equal to scorer. So once I done this, then obviously the tuned model is height mod. I want to fit it dot fit of my x train comma y train. Now you can see it is actually running, right? So previously while we do linear regression, only we usually do tune alpha. So just like that it will happen. Now you can see. So it's taking a lot of time because n estimator we have given different number for each and every number. It also explore with max feature and max depth. So ultimately it takes some time. So that is the reason why I have not typed other parameters for now there. But anyway, while you are building your model, you can try for building or giving all those options. This is also one another reason why I have told like tuning individually also it's very important, because once if I confident, once I'm just trust this analysis that I did with respect to variance error and bias error for n estimator, there is no need for me to tune here with all the combination of n estimator. Here just to check once again, I'm just tuning it. But once I'm comfortable with the way that I have did the tuning with respect to that for loop for that n estimator, once again I no need to tune it here. I will just keep that one single number here itself. I just keep only 25 here, and with respect to the 25 as an n estimator or with respect to 80 as an n estimator, I will explore other things here. I will explore other things here. That actually save my time, right? See, now I have to wait for lot. I have to wait for more time to get this output. But anyway, you should have time to spend some time to do this hyperparameter tuning, because this is one-time process, right? You are not going to do this on the test side. Even though if you are sometime it takes even few hours to tune your model, tune it. So once you have the final model, you can dump it using Pickle or any other package. You can dump that final tuned parameter in your hard drive. So at any point of time, you can take and reproduce to test your data. So obviously, training will take a time, especially with respect to the hyperparameter tuning with random forest, where we are tuning so many things. Will take a lot of time, as we are witnessing here. It's just still running. So anyway, I have given the code part in your chat window too. Please try in your mission also. Maybe if your mission is a little bit fast, it will happen in a little bit quick way too. So this is the flow as usual for all the other algorithm. We have to just build the model, and we have to understand the model, and we have to tune the model. Of course, that understanding part here with respect to the random forest, the same thing. So in our last session, we have spent more time on feature importance and tree interpreter, right? So that the two things what's here also. Feature importance will give you what is the overall feature significance for that whole model with including all the trees. Whereas tree interpreter, while you are passing one particular observation into your model, what is the impact of each and every feature on the output, that you can understand through the tree interpreter. So whatever the thing that we have discussed with respect to tree interpreter and feature importance can be applicable as it is on this random forest model also, right? So this is what the different thing that I thought of discussing with you. So once it's over, I think it's now over, right? So just I can see what is my best param. I can see that max feature log 2 and n estimator, surprisingly here it is coming as 45. Just go and check. But of course it is actually doing the cross val score, but previously also it's cross val score. 45 means somewhere here, no? So you have to run this loop once again for 45 also here. We have run for 40, then we have jumped to 50. But here research CV is giving with respect to something with respect to 45. But anyway, the problem with research CV is it's giving these numbers only with respect to the bias error. It is not actually seeing the variance error at all. So that could be the reason. With respect to the bias error, 45 is n estimator is giving you the less bias error. But what about the variance error? We also see the variance error, right? So that is the exact reason why we have done with the for loop. Otherwise, here also you can see the CV2 results. So like tune mod dot CV2 results, PD dot data frame. Just printing only the top 5, something like that. Top 5.
FRAME, sir. Yeah.
Right, so now you can analyze this last column, like whatever I have plotted, like that you can plot for standard test score and mean test score. All right, so now previously I have plotted with respect to variance error and bias error for that for loop result. Now you can plot this mean test score and standard test score. By seeing that plot, you can make the decision for which n estimator or for which hyperparameters your model is doing well. That you can actually keep as an best param. But here that best param is given with respect to only bias. You can plot this mean test score and standard test score to understand it further in terms of variance error also before taking the final decision on your best parameters. Right? So this is what the thing that I thought of discussing with you today. I think Lina, I think now you can release the poll.
Sure, sir. Sure.
Yeah.
Sir, I gave all the questions, all the 4 questions.
All the 4 questions did we cover?
I think one is on features of decision tree, minimum samples. Then I think bagging not covered, no, sir.
So bagging I have covered.
Hyperparameters in the number of trees in random forest.
Yeah, we have covered all those things. I think you can release.
Function of ensembling also. No?
Yes.
Okay, sir.
Fine. I think we can quickly discuss the result of that poll. I think everyone attempted that. Let us discuss that. So the first question is, which of the following statement is not true? So minimum sample split hyperparameter will have the information about the minimum number of samples required to split a node. So what your take on that? Whether it's a true statement or a false statement? The first statement. Minimum sample split is an hyperparameter will have the information about the minimum number of samples required to split a node. True or false?
True.
It's true, right? So minimum sample split is actually telling like how many samples we need so that it can be further splittable. So that is true. The second statement is minimum sample leaf provides the information about the minimum number of samples required to be at leaf node. Exactly. So if you want something to declare as a leaf node, at least this many samples should be there in it. So that is also a true statement. And the third statement is, if max depth is none, then this value will be decided based upon the minimum sample split. So obviously, if you are not giving max depth with any value, then obviously the max depth will be decided by the minimum sample split, because once that minimum sample split criteria has been reached, once I am giving the minimum sample split as 10, so once in one particular node, the number of samples will become 10. So obviously your it is not going to be further splitted, right? So that max depth is having some kind of relationship with the minimum sample split. So that is also a kind of true statement. Then what is the next statement? A model with minimum sample split equal to 2 will avoid overfitting. So do you think that the final statement is true? Minimum sample split equal to 2 means what?
It's overfitting.
It's an overfitting, right? Even we are allowing that split to be happen, even if the minimum sample split value is equal to 2. So if you want only 2 points or only 2 samples are there in one particular node, we are still allowing that to split. So it may even become 1-1. So that is a kind of overfitting model. So we'll avoid overfitting is the wrong statement. So the last answer is actually not true. Then the next question, which of the following statement is wrong about bagging and random forest? So row sample technique is used in bagging. True or false?
True.
True. So in bagging, obviously bootstrapping, we are using. So row sampling technique is nothing but that bootstrapping, taking that random samples out of it with replacement. So it is true. Row sampling techniques used in random forest. True or false?
True.
True.
True. Because in random forest also we are using the same bootstrapping thing. Column sample techniques used in random forest. True or false?
False.
True.
True.
Oh,
True.
true. Right? Even we have a max sample, a max feature we have used now in hyperparameter. I told that the difference between bagging and random forest is in random forest, both row sampling as well as column sampling is there. Randomness we are actually generating through selectively taking rows and also selectively taking the columns. So column sample technique is used in random forest is true statement. Column sample technique is used in bagging. So generally we don't
False.
use
False.
column sampling in bagging, only row sampling in bagging. So that is false. But actually, if you see the sklearn bagging is providing one option for that newer version. I don't know why, but anyway, bagging by theory, by literature, bagging will use only the row sampling, not the column sampling. So that last statement is actually wrong. Then third question, which of the following hyperparameter is deciding the number of trees in the random forest?
N estimator.
N estimator.
Max step. Oh,
Sorry?
nothing, sir.
Yeah. So N estimator, I think N estimators, there is spelling mistake. But anyway, N estimator, N tree, we don't have something like that as an hyperparameter. Max depth is also, it's actually It's there as hyperparameter for random forest, but max depth is for some other purpose, right? So and also max feature is there, but that is also for other purpose, like introducing the randomness, reducing the overfitting, using max depth, how long the tree can grow. But n estimator is talks about how many trees should be there in our model. So n estimator is the answer for the third question. And for the fourth question, what is the function of ensembling techniques? The first statement is, it is a process of selecting one optimal model out of many submodel. Is it the objective of ensembling technique?
No.
No. So it is not like we are going to say we are going to construct multiple trees and we are going to select one good tree out of that n tree. That is not the objective of ensembling. Then the second point is, ensembling is the process of producing the best model through hyperparameter tuning. Is that tuning? During the hyperparameter tuning, we are calling as an ensembling?
No.
No.
No. Right? Hyperparameter tuning is something else. That is not is common for all the model, right? We are not calling that as an ensembling. So the third one is, ensembling is the process of combining multiple base models to produce the best predictive model. Is that true?
Yes.
Yes.
True.
Yes.
Yes. So combining, there are so many multiple models. Each and every multiple base models are coming up with its own opinion. We are actually ensembling it, and we are actually producing the one best predictive model by using all those base models. So of course, in what way, max vote and all those things we have discussed. That is what the main objective of ensembling. So ensembling technique will produce the result through one optimum model. That is not true, because ensembling technique will produce by combining the results of all the models. It is not actually taking the results or taking the final result using one single base model. It is actually multiplying, or it is actually manipulating the results of all the base model, and with respect to that, it is taking that one single decision. So the third option is the correct option for this. So this is what about this poll questions. If you have any other general queries with respect to whatever we discussed in today's section, you can ask me now.
Sir, we applied smart analysis for predictor, right? So instead of that, consider if any one of the input feature as 1:9 ratio dataset a binary class, can we apply smart to that? Or is it only for the y variable we should apply?
No. So that smart will work with respect to the target only. But that your question is, what if in input variable, like say one categorical variable is there, in that categorical variable, one level is representing 90% of data, the another level is representing only 10% of data. That is what your question, right?
Yes, sir. Yes, sir.
So for that, we can't actually really do the sampling, right? So with respect to what input you will do that. If you apply smart, you need to have a data distribution with respect to that output column, that plane that we are forming, that KNN and all I have explained, nearest neighbor and all those things, that ultimately will actually generate the, with respect to this output column, I am just synthetically creating the input columns. Now if input column itself it's not having the balance, so you can't keep that input column as a target column. With respect to that target column, you can't create some new other columns, right? Because there is no necessity that one input column is need to have some kind of relationship with the other input column. So there is no point in doing smart with respect to one input column imbalance. So if one input column is like that, one level is actually representing 90% of the data, the other level is representing only 10% of data, you have to apply some kind of chi-square test or some kind of statistical test, or you have to plot the distribution with the target. With that target, if it is not discriminative enough, then you have to drop that column. You have to drop that column because that input is not explaining anything reasonably well about the output, because out of that 100 data, 95 observations belongs to the same value. Say qualification in that BE and ME is there. Out of that 100 observation, 95 observations are BE, only 5 observations are ME. You have to relate that with the target column and see whether that 5 ME column is having some class label which is actually different from the other 95 column. If not, that you can get it through your chi-square test. If these two columns are not actually related, then obviously you have to drop that. You have to drop that input column, because machine learning model is not going to learn anything, because that is the true nature of the data. You should not do the sampling to make that balanceness.
Okay, sir. Got it. Got it. Thank you.
So it is only for the output column.
Okay. Okay.
Any other queries?
Yes, sir, I have doubt. So,
Yeah.
so from input data, we are taking sampling, right? So the sample is which type of sample? It is random sample or any stratified sampling? Should we give the any weightage to this sampling like that? So it's
Where-
randomly picking, right?
Yes, randomly picking what in SMOT you are talking about?
Not small from overall data. See, if data is 100 samples, so from 100 samples we are taking 60 and we are doing sampling from 60. So
Okay.
60 to 100 is sampling. So which type of sampling is doing, like randomly is doing or any stratified sampling or any type of?
No,
So if
you are asking about this yes random
Sampling.
forest, like in
Yep.
random forest, while it is taking that 60 sample.
Yeah.
So it is actually randomly only doing. So we don't want any kind of pattern there. Only if randomly it has the ability to split with replacement, then only we can able to bring that genericness in our model. So it is simply doing some kind of random sampling. So you can freeze that seed by using some kind of random state, but it is not specifically using any kind of sampling strategy. Of course, internally, if you decode it, definitely to do some any kind of sampling, if you need to do, people will use some kind of strategy behind it. But generally, we no need to much worry about it. Our objective is, I want my model to pick those numbers in a very random way, in a high random way. Then only my machine learning model will learn these stuffs in a generic way. So that is the reason why they are not even given that as a kind of hyperparameter to us, right? So we have to just concentrate on how many samples you need to pick. That is available as a random hyperparameter for us to control it. So it need to pick that in a random way. So even though it is picking in a completely random way, my model is learning, right? So that is the kind of generic thing that I want to feed into my model. So it is not that my model need to work well with this kind of sampling strategy, but for some other kind of sampling strategy, it may not produce the same performance. I don't want that kind of bias towards my model. My model need to do well irrespective of whatever the section of data that I have give for that to work. It should work and it should produce the performance. So in that way, it's a kind of random thing, but internally if you want, you can go and see the GitHub code for this sklearn random forest classifier. You can see the backup code for all those functions, so where you can get the idea of what kind of strategy that they are actually using.
Okay, sir. Yeah, thank you.
Any other queries?
No, sir.
Students, you were able to see the solutions, no? For the solutions were uploaded. Okay, please check it. The solutions which were uploaded for the
Yes, ma'am, it
in-class.
is uploaded.
Sir,
you,
in the last quiz we have one question like about data mining.
In the quiz part, no, Raghu?
Crisp, cross data, in the quiz. I don't know, actually not discussed that thing, but crisp and cross.
It is in the deck, Raghu, the first deck which was uploaded. The crisp DM, sir.
Yeah, that one I think it's not discussed in that.
You can raise a support ticket, Raghu.
So what is that, Lena?
The CRISP DM, no sir. The flow of CRISP, sir. CRISP DM.
Okay.
So they had asked a quiz question on that.
Okay. So that is kind of theoretical thing, right? So
Yes, sir. Yes.
That is which algorithm is there?
Yeah, Raghu, you can raise a support ticket.
Okay, just I'm asking. So that belongs to which topic? That topic, which algorithm? Like logistic?
that is not different algorithm, something like that. That is a kind of generic kind of flow standard, something like that.
Okay, okay,
Algorithm, something like that.
okay, sir.
Yeah.
Okay, sir. Thank you.
Any other questions, class?
No, ma'am.
Thank you, Raghu. Sir, can
Fine.
we bind? Yeah.
Yeah, sure. Sure. Thank you very much, guys. Thank you, Lena.
Thank you, sir.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.